Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. It begins with warmth. A gentle golden light caresses your closed eyelids and brushes your skin. You inhale, feeling the soft heat of sunlight that has traveled across empty space to reach you. In this quiet moment, the sunlight feels almost alive, a tender presence on a cool morning. You might take it for granted, this glow on your face, but it is the gift of an immense power. High above, the sun hangs in the sky, pouring out light and warmth in all directions. Now imagine following that warmth back to its source. Drift upwards, leaving the ground behind. The light grows brighter. Blue sky fades to black as you rise beyond Earth's atmosphere, and the sun's true face comes into view. A brilliant star burning in the dark. Here, hovering in space near the sun, there is no air to carry sound, only silence. Yet before you stretches an enormous sphere of glowing plasma, its surface, a roiling ocean of fire. Tongues of flame and loops of energy dance at the edges, solar flares arcing outwards, but you hear nothing at all. This close, the sunlight is blinding and the heat is ferocious, but space itself remains eerily still and quiet. Inside the sun's core, countless atoms fuse each second, releasing prodigious energy. Photons born in that deep furnace begin a long random walk outward, bouncing through dense stellar material for ages, before finally emerging at the surface as the warm light we know. When they break free, they rush into space at last, racing at light speed. Only about 8 minutes later, some will kiss a human face on a distant blue planet. But here at the source, you float in the glow of creation itself. The sun's surface seethes with granules and magnetic storms, yet from a few million miles away, it looks tranquil. A perfect, bright orb hanging in the void. A crown of wispy solar corona surrounds it, visible as a faint halo. Fine streams of charged particles, the solar wind, flow outward, but you cannot see them. Only feel their faint whisper, if you could hold out a hand. This star, so loud in its nuclear heart, offers its energy to the solar system in utter silence. You turn slowly away from the sun and begin a long spiral journey outward. The light at your back diminishes a little with each passing million miles. Ahead lies the domain of planets, tiny islands of matter circling the parent star. The first island appears very soon. Mercury, the innermost planet, emerges from the glare. Mercury is a little round world of rock and metal, so close to the sun that it's been baked bone dry. As you approach, you see a globe that looks strikingly like Earth's moon, grey, heavily cratered, and airless. Long ago, impacts pockmarked its surface with craters of all sizes, and there have been no winds or rains to soften them. Daylight here is harsh. The sun looms more than 3 times larger than it does in Earth's sky, and the ground under the sunward side blazes under intense heat. You can almost feel it radiating off the cracked regolith. The rocky ground expands and cracks from the scorching temperatures. But Mercury rotates extremely slowly. One day lasts 2/3 of its year. So one side broils in endless daylight, while the other side, long without sun, cools to frigid darkness. In the black sky above the sunlit surface, the stars are visible even at noon, because there is no atmosphere to hide them. If you could stand on Mercury at midday, the sun's fierce light would pour down from a pitch-black heavens. And when night finally falls many Earth days later, it brings a cold more intense than any winter, freezing the ground solid as the heat radiates away into space unimpeded. As you drift low over Mercury's surface, you notice bright streaks around some craters, rays of ejected dust from ancient impacts. You also see great curving cliffs, hundreds of miles long, that cut across craters and plains. These scarps formed as Mercury's interior cooled and shrank, wrinkling the surface like a dried apple. Mercury is astonishingly dense for its size. Deep below, it holds an outsized iron heart, a metal core taking up most of the planet's volume. That heavy core and the sun's gravitational grip keep Mercury locked in a strange dance. It spins 3 times for every 2 orbits around the sun. In Mercury's polar recesses, where the sun's rays never quite reach, there are deposits of water ice hidden in eternal shadow inside craters. It seems impossible, yet even at the sun's doorstep, frost can exist in the dark. Mercury is a world of extremes: blazing day, airless night, searing sun, and hidden ice. It is the innermost sentinel of the sun, a little cratered enigma racing around the star every 88 days. You leave Mercury behind, a tiny scorched globe receding into the brilliance, and journey outward to the next planet. As the sun's glare lessens a bit more, a pale yellow-white beacon appears ahead: Venus. From a distance, Venus is breathtaking, a perfect pearl of a planet, swathed in thick white clouds that reflect sunlight brilliantly. It outshines everything in the night sky, but the moon, a lovely evening star. Yet that beauty hides a deadly secret. Dropping down toward Venus, you penetrate its cloud layer and enter a smothering world of golden twilight. The atmosphere here is a dense broth of carbon dioxide with clouds of caustic sulfuric acid droplets. The further you descend, the darker and more orange the light becomes, tinted by the thick haze. Venus's clouds form an ever-present global blanket, so the surface knows nothing of stars or blue sky. Only a dim, diffuse illumination under eternal overcast. Deeper and deeper you go, and the pressure mounts. At the surface, the atmosphere presses down at 90 times the pressure of Earth's, like being 900 meters under the ocean. The air is a supercritical fluid, almost syrupy in its density. Here, a human would be crushed instantly. And the heat is astonishing. The temperature near the ground is hot enough to melt lead and zinc. The rocks themselves glow faintly dull red from the furnace-like environment. There is no water. Any that Venus once had boiled away eons ago in a runaway greenhouse inferno. In the dim light, you make out a barren landscape. Rolling plains of volcanic rock. Sharp-edged stones under an orange sky. The terrain is strangely quiet and still. No rain ever falls. No wind stirs at ground level. The air is too heavy. Only far above, at the cloud tops, do high winds race around the planet, shrouding it in fast-moving storms that never touch the hellish ground below. Volcanoes dot the surface, some enormous shield volcanoes bigger than any on Earth. Much of Venus appears to be covered in vast basaltic plains from ancient eruptions. In some places you see fields of strange domes and arachnoid patterns, volcanic landforms crushed and contorted by the intense pressures. The ground shows evidence of past lava flows and perhaps current volcanism, fresh-looking basalt, and signs that the planet may still be geologically alive. But if volcanoes erupt here, they do so in utter secrecy beneath the perpetual cloud deck, their red glow absorbed by the choking haze. The heat on Venus is unrelenting and nearly uniform across the planet, day or night. Venus turns so slowly on its axis, it takes longer to rotate once than to orbit the Sun, that a single Venusian day lasts almost 4 Earth months. But the thick atmosphere evens out the temperatures, carrying warmth to the night side. It is a world in slow motion, skies forever darkened by cloud, surface baking in constant dusk. For billions of years, Venus has known no relief from this self-made purgatory. Long ago, perhaps, it might have had shallow seas and milder air before something went terribly wrong. Now it stands as Earth's twisted sister, nearly the same size and composition as our home, yet completely inhospitable, a vision of a greenhouse nightmare. The only hints of anything gentle are far above, about 50 kilometers up. In the upper cloud layers, the temperature and pressure are nearly Earth-like. High in those clouds, strange streaks and patterns have been observed, perhaps just chemistry and droplets. But some have speculated about airborne microbial life surviving in the temperate heights, living in acid droplet clouds. It remains only a tantalizing idea. Leaving Venus, you ascend back through thick orange clouds that thin to bright white and finally break into clear space above. The planet's shining veil closes beneath you, hiding that toxic surface once more. You are glad to leave the crushing pressure and stinging acid behind. Out here above the clouds, Venus looks serene again. It is hard to imagine the inferno lurking below that placid cover. With a silent farewell to the morning star, you journey onward. The sunlight now is gentler, more golden, as you approach the orbit of Earth. Soon, a jewel appears in the blackness, a blue marble adorned with swirls of white. Our home, Earth, reveals itself in full sunlit glory, a sight to fill the heart with wonder. From space, Earth is a vision of vibrant color, deep sapphire oceans, bright tan deserts, verdant green-brown landmasses, and above them, swirling white cloud formations. A delicate film of atmosphere encircles the planet as a thin, glowing blue rim at the horizon. Compared to the harsh, airless moon or the choking blanket of Venus, Earth's atmosphere is a tender and life-sustaining mix, just thick enough to spread warmth and allow weather, transparent enough to let sunlight nurture the surface below. You descend toward the Earth, and as you slip into the atmosphere, you feel the first tug of aerodynamics, hear the faint whistle of wind. Thin, high air grows to a breathable breeze. Puffy white clouds drift below, casting soft shadows on the oceans. You pass through a layer of wispy cirrus and emerge over a vast expanse of ocean. Sunlight dances on waves that roll and break in white foam. The air is sweet and carries the scent of salt and living things. Seabirds wheel and cry beneath you as you skim just above the waters. Unlike any other planet in our solar system, Earth's surface is mostly liquid, an ocean world where life began in warm primordial seas. The blue expanse seems endless and calming. Moving over a coastline, you see green forests hugging the shores and brown mountains further inland, capped with snow. Rivers sparkle in the sunlight, winding from highlands down to estuaries, carving valleys over eons. In the forests and plains, every patch of Earth is alive, a tapestry of life forms in every shape, each contributing to the grand harmony of the biosphere. You sense activity and energy everywhere, the flutter of leaves in the breeze, the chirp of insects, the distant roar of a waterfall, perhaps even the murmur of human civilization if you listen closely. Faint hints of voices or engines far below, nearly lost in the vastness. Earth is alive both geologically and biologically. Its crust continually renews itself through plate tectonics. Continents drift imperceptibly, colliding to thrust up mountain ranges and pulling apart to create new ocean floor. Volcanoes occasionally pierce the surface, bringing up nutrients from Earth's depths, and earthquakes remind us that our planet's skin is restless. And Earth is alive in another sense. It hosts a biosphere that has transformed the air and land. Green plants inhale carbon dioxide and exhale oxygen. Animals do the opposite. Life and Earth dance together, each shaping the other. The atmosphere you breathe, rich in oxygen and balanced with nitrogen, exists only because countless tiny organisms in the ancient seas produced oxygen as a waste gas over billions of years. Now forests and phytoplankton maintain that balance. The result is air that allows both intense activity and gentle breezes, clouds and rain, climate and seasons. Earth sits at just the right distance from the sun, not too hot, not too cold, allowing water to remain liquid at the surface, cycling perpetually from ocean to cloud, to rain to river, and back to ocean. This endless water cycle weaves weather and nourishes life. On the day side, Puffy white clouds gather over tropical seas, releasing afternoon showers. In the night, thunderstorms flicker over equatorial lands, illuminating clouds from within with lightning's glow. Polar auroras shimmer occasionally at the highest latitudes, painting the sky with silent curtains of green and red light when solar particles strike Earth's magnetic field. High above, Earth's magnetic field forms an invisible shield, deflecting dangerous charged particles from the sun, ensuring the surface is not stripped of its atmosphere or sterilized by radiation. This magnetosphere funnels some particles to the poles, where they create those auroras, a gentle, beautiful side effect of our planet's protective embrace. Circling the Earth is its constant companion, the Moon. As you move around to Earth's night side, lit now only by starlight and the silver glow of the Moon, you gaze up from an earthly hillside at the lunar disk. The Moon hangs in the sky, airless and silent, shining by reflected sunlight. This grey orb has been a beacon for humans for as long as we have existed, its phases marking the passage of months, its gravitational pull quietly stirring our ocean tides. You decide to visit our Moon, rising off the Earth's surface once more and gliding toward that familiar cratered globe. In hours you arrive, settling down onto a vast lunar plain. The scene is otherworldly. The ground is covered in fine charcoal-colored dust, undisturbed save for ancient meteorite craters and, in certain spots, the faint tracks left by human explorers. Here on the Moon, the sky is pure black even when the sun is up. The harsh sunlight casts inky shadows among the rocks. You notice footprints pressed into the powdery soil, footprints left by Apollo astronauts half a century ago. They look as fresh as if made this morning. With no atmosphere here, there is no wind or rain to ever erase them. They could remain for millions of years, silent testimony to humanity's reach. The Moon's landscape is starkly beautiful in its simplicity. Rolling plains of solidified lava called Maria, lighter highlands densely cratered by impacts, and the pitch-black shadows inside deep craters near the poles where sunlight never shines. In some of those craters, scientists have discovered ice mixed with the soil, delivered by comets and preserved in the perpetual cold of shadow. You gaze back toward Earth, a blue marble now rising above the Moon's horizon. The Earth is many times larger in the lunar sky than the Moon is in Earth's sky, and it hangs almost motionless because the Moon keeps one face always turned toward us. A dazzling halo of blue and white, our home planet looks alive and fragile from here, suspended in space, half illuminated. It casts a gentle pale glow across the lunar ground. Earthshine, lighting the night portions of the Moon, just as moonlight illuminates Earth's night. The connection between Earth and its Moon is profound, gravitationally locked in an ancient dance, each affecting the other. The Moon's pull raises the ocean tides on Earth, and perhaps helped stabilize Earth's tilt over geological time, smoothing the seasons. And Earth's gravity, in turn, raised enormous tidal stresses in the young Moon that may have shaped its early volcanism. Climbing back into space, you leave the Moon's silent regolith and continue outward. You have now passed the Sun's first two inner worlds and Earth with its satellite. Next in line is Mars, the red planet, glowing with a rusty hue in the distance. Approaching Mars, you find it smaller than Earth, about half the diameter, and wrapped in a much thinner atmosphere. Its ruddy color comes from iron oxide, essentially rust, in the dust that covers its surface. Once you enter the Martian atmosphere, you realize how tenuous it is. Just a faint whisper of carbon dioxide gas, less than 1% the density of Earth's air. The sky here has a butterscotch tint, tinted by fine dust suspended high above. In the daytime, the sun is a bit dimmer and smaller than on Earth, its warmth far weaker in the thin air. You drift down to the surface near the Martian equator, landing on a broad reddish plain strewn with rocks. The ground is covered in reddish sand and dust that clings electrostatically to everything. In the far distance, a colossal mountain rises. Olympus Mons, the largest volcano in the solar system. Its huge bulk so wide and gentle sloped that from here you might not realize you're looking at a mountain at all, but it towers many kilometers above the surrounding plains. In another direction, you see a great canyon system cutting across the landscape, Valles Marineris, a chasm that would span from Los Angeles to New York if it were on Earth, and several times deeper than the Grand Canyon. It rends the Martian crust with steep cliffs and layered walls, colored ochre, gold, and red. This immense scar speaks of tectonic forces or something that nearly tore the planet apart long ago. The air is deathly still. Occasionally a light breeze may stir some dust, but Mars's atmosphere is usually eerily calm. Yet at times it can erupt. Global dust storms have been known to engulf the entire planet, turning the sky a tawny brown for months. But on this day, it is tranquil. The temperature is cool, near freezing at noon, but will plunge far below freezing after sunset. Overhead, the sky is a yellowish brown near the sun, fading to a deeper blue-gray at zenith. There are wispy clouds of ice occasionally, and in the late afternoon, you might even see a delicate streak of cloud catching the sun. Mars is a desert world, cold and dry. But as you wander, evidence of water is all around you in the shapes of the land. You float over an ancient river valley, now completely dry, its once sinuous channel carved into the rock. Long ago, water, actual liquid water, flowed here, possibly in rivers and lakes. You spot what looks like an old delta where a river met a basin, the telltale fan shape of sediment. And that great canyon, Valles Marineris, may have been enlarged by water flowing out from underground. Today, however, Mars is a freeze-dried world. The only water you see lies locked up as ice. Caps of bright white at the poles gleam against the rusty terrain, composed of water ice and carbon dioxide ice, dry ice, that grows and shrinks with the seasons. Just beneath the surface at these latitudes, a permafrost of ice extends for miles. The sun is setting now on Mars. In the west, the sun descends as a small bright disk, and the sky around it turns coppery. Curiously, just as the sun drops below the horizon, the sky directly above the setting sun glows a cool bluish tint for a few moments, a quirk of how the fine dust particles scatter blue light more efficiently when the light path is long. Twilight on Mars is blue. Soon, the first stars prick through the sky, and an intense cold permeates the thin air. In the darkness, you notice two tiny moons rising. Phobos, the larger, is a misshapen rock only about 22 kilometers across, looking more like a big asteroid than a proper spherical moon. It orbits Mars with dizzying speed, crossing the sky from west to east in just 5.5 hours. Deimos, smaller and farther, appears as a star-like point of light. These moons are likely captured asteroids, pilfered by Mars's gravity long ago. Phobos hangs so close that in some regions of Mars, it would appear to dart overhead multiple times each day. Its surface is dark grey and heavily cratered. A large crater named Stickney gives it a somewhat skull-like appearance. Someday Phobos will spiral inward and break apart or crash into Mars. But for now, the two potato-shaped moons silently circle their rust-colored master, witnessing the red planet's lonely desert sunsets. Mars feels like a world on the cusp, a once active planet, now largely asleep. Long ago, it had volcanoes that built towering mountains and water that carved channels through its soil. Something changed. The volcanoes grew quiet, the water froze or escaped, and the atmosphere thinned to nearly nothing. Now it waits, an enormous and silent desert, tinted red by the oxidized dust of ages. Still, it beckons us with its similarities to our own world: polar caps, day lengths and tilted axis that give it seasons like Earth's, though colder, and a geology that speaks of processes familiar yet extinct. In its soil and rocks, perhaps microbial life once took hold in the wetter past. Perhaps even now some hardy remnants survive hidden beneath ground, clinging to warmth and moisture. Mars keeps its secrets for now, whispering them in dry winds that occasionally skip dust devils across the plains, dancing columns of dust that briefly snake upward before dissipating. You watch one of these dust devils swirl in the distance, tracing a delicate path and leaving dark streaks where it cleared the reddish dust off the surface below. Then it's gone, and stillness returns. You have now traveled roughly half the length of the solar system's planetary zone. Ahead lies the vast expanse beyond the inner rocky worlds, a domain of giants and mysteries. As you depart Mars, you traverse the boundary between the inner and outer solar system. The sun is smaller now behind you, though still bright. Moving outward, you enter a wide region populated not by singular planets, but by countless smaller bodies, the asteroid belt. This torus of debris stretches between Mars and Jupiter, filled with remnants from the solar system's formation. Contrary to Hollywood depictions, the asteroid belt is mostly empty space. The asteroids within are separated by hundreds of thousands or even millions of kilometers. You could drift through and likely never encounter one unless you deliberately navigated to it. But imagine you could see all these rocks at once, speed up time, or put them all before you. You'd behold a vast swarm of ancient mountain-sized boulders and smaller rocks, each tumbling in the sunlight, casting stark shadows on themselves. Some are solid metal, shiny nickel-iron fragments of long-destroyed protoplanets' cores. Others are porous rubble piles of rock and dust, only lightly held together by gravity. Most are irregular, cratered from countless collisions with their brethren. These are the leftovers that never formed a planet, perhaps due to the disruptive gravity of nearby Jupiter. You pass one of the largest asteroids, Ceres, a dwarf planet roughly 950 kilometers wide. From a distance, it looks almost spherical, a dull grey world with bright salty white patches gleaming within some craters. Those bright spots mark places where briny water or slush oozed up from Ceres's interior and deposited reflective salts upon evaporating, evidence that even this small body has or had a subsurface ocean, or at least pockets of liquid in its past. Ceres is a gentle world with a light gravity. Long ago, it may have been warm enough inside to differentiate into layers. Today it's cold, but still may hide slushy mud or ice deep down. As you glide low over one bright crater named Decatur, you see the ghostly shimmer of those salt deposits, remnants of cryovolcanism that happened within the last few million years, nearly yesterday on geological timescales. Ceres, quiet now, hints at activity not so very long ago. Farther on, you pass by an oddly angular rock. It's Vesta, another giant asteroid, with a huge gouge at its south pole from a titanic impact. That impact blasted out enormous quantities of debris. In fact, many meteorites that fall on Earth are pieces of Vesta, identified by their unique mineral signature. Vesta's surface is a patchwork of light and dark areas, ancient basaltic lava plains and brighter highlands. It almost became a planet. It has a core and mantle like one, but it never grew quite large enough. Scattered through the asteroid belt are countless smaller bodies, like little Ida with its tiny moon dactyl or metallic Psyche, shining faintly as it tumbles end over end. Occasionally, two asteroids have collided and shattered, and you see their fragments following similar orbits, family groupings of rubble slowly dispersing over eons. In this region, the echoes of creation and destruction linger on every scarred surface. It's serene now, but the belt's history is violent. The asteroids we see are the survivors of an early era of frequent collisions. Even today, once in a while, asteroids still collide, and the impact sends out showers of debris. Some of that debris might eventually wander inward as meteoroids and sometimes reach Earth, flaring as shooting stars or meteorites on the ground. Coasting outward through the asteroid belt, the sun continues to shrink behind you. The inner planets are now tiny dots lost in a brilliant solar glare. Ahead, an entirely different kind of planet awaits, the first of the gas giants. Jupiter grows from a star-like point to a visibly disk, then to an immense striped globe dominating your field of view. You have arrived at the king of planets. Jupiter is staggering in its size. Over 11 Earths could be lined up across its face. As you come alongside it, you feel dwarfing humility before this banded colossus. Its upper atmosphere is patterned with broad bands of white, ochre, and reddish-brown wrapping around the planet. These are rows of clouds driven by powerful winds that roar east-west at hundreds of kilometers per hour in opposite directions for adjacent bands. The lighter bands, called zones, are higher clouds of ammonia ice, while the darker belts are deeper layers where other chemicals give ruddy and yellow hues. The boundaries between belts and zones are turbulent, with eddies and swirls where the opposing winds shear against each other. One feature stands out especially on Jupiter's canvas: the Great Red Spot, a titanic storm twice as wide as Earth. This oval tempest has been churning in Jupiter's southern hemisphere for at least 350 years, since humans first observed it through telescopes, and likely far longer. Within its brick red oval, winds howl counterclockwise around a high-pressure center, and ammonia clouds pile high. It is a cyclone of enormous proportions, its outer edges flaked by smaller vortices. As you hover above it, you see the spot's color has softened to a coral or peach tone nowadays, and it has shrunk somewhat compared to historical records. But it is still a vast, persistent hurricane beyond any earthly scale. We could drop our whole planet into it with room to spare. Lightning crackles elsewhere on Jupiter too. Near the poles, bright white thunderstorms erupt from deep water cloud layers, occasionally illuminating the cloud tops with brief flashes. Jupiter's atmosphere is dynamic and alive with activity, a ceaselessly roiling artwork of fluid physics. There is no solid ground for you to land on here. Jupiter is likely composed mostly of hydrogen and helium gas, with increasing pressure and density as you go down. If you descended through those clouds, the atmosphere would thicken into a hot soup, eventually into a fluid state, and deeper still perhaps into metallic hydrogen that conducts electricity like a metal. Far below that, somewhere in the crushing depths, may lie a dense core of rock and ice perhaps, but no human-made probe could survive long enough to reach it. Instead, you remain high in the atmosphere, skimming along the cloud tops at a safe distance. The view is magnificent. It's like floating above an unending cloud ocean, with rolling formations and whirls the size of continents. Long, snaking cloud bands trail around, and small oval storms, white or brown, dot the belts, each one a cyclone or anticyclone. High-altitude haze in places casts shadows on lower cloud decks. Over the poles, which were unseen by any human until recently, you would find swirling clusters of cyclones arranged in geometric patterns. Immense polar vortices, with unexpected symmetry, quietly rotating in the dim sunlight at high latitude. Jupiter is more than just a planet. It's almost a miniature solar system of its own. Circling around it are dozens upon dozens of moons, a retinue of diverse worlds bound by Jupiter's mighty gravity. 4 of those moons are so large and intriguing that they draw nearly as much interest as the planet itself. If you drift outward a bit to a vantage where you can see Jupiter's entire system, the 4 Galilean moons line up like tiny disks orbiting in the plane of Jupiter's equator. Innermost is Io, a moon about the size of our moon, but painted in vivid mottled yellows, oranges, and black. Io is the most volcanically active body in the solar system. As you approach Io, you notice strange blotches and sulfurous colors on its surface. Those are volcano calderas and deposits of sulfur compounds. Suddenly, on the terminator, the line between day and night, you catch sight of a towering plume, a volcanic eruption in progress. A fountain of sulfur dioxide gas and dust is blasting out of Io's surface, arcing high into space to an altitude of several hundred kilometers before the frost of space causes it to snow back down. Io's gravity is low, so these plumes form umbrella-like canopies, like giant blooming flowers of smoke. The moon's entire surface is constantly repaved by lava flows. Lakes of molten sulfur glow red in the dark, and fresh lava plains cool to dark crusts. Io's intense volcanism is powered by Jupiter's relentless tidal grip. The giant planet's gravity flexes Io's interior as the moon orbits, generating heat by friction and melting Io's insides. No impact craters are visible on Io. Any that form are quickly buried under new volcanic deposits. The air is extremely thin, just a wisp of sulfur dioxide, but enough to freeze at night and form a faint transient atmosphere by day. Io is a tortured world of fire and brimstone, literally a moon on fire under Jupiter's gaze. Next out is Europa, only slightly smaller than our moon. Europa's surface is strikingly smooth and bright, crisscrossed by long reddish-brown streaks like cracks on an eggshell. That analogy isn't far off. Europa is encased in a shell of water ice, perhaps 20 kilometers thick, and beneath that ice lies a global ocean of liquid water. It's hard to believe at first. You stand on a world so cold that ice is rock, yet beneath your feet is likely a deep saltwater sea kept liquid by tidal heating from Jupiter's pull. Europa's surface tells a tale of this hidden ocean. The network of streaks and cracks suggests that the ice crust is continually fractured and shifted by tides, and occasionally water or slush wells up through the cracks to resurface the moon. Hardly any craters mar Europa's surface, implying it is young and continuously renewed. At a few spots, you see what might be small plumes, geysers of water vapor, venting into space through fissures in the ice, evidence that sometimes the ocean below can communicate with the vacuum above. The sunlight here is weak, and the surface is bitterly cold, around 160 degrees Celsius. But the ocean below, sealed under the ice, might be a comfortable temperature, and likely completely dark, except perhaps for faint glow from any hydrothermal vents on the ocean floor. Yes, deep down, at Europa's rocky core ocean interface, tidal heating may drive undersea volcanoes or hot springs, providing chemical energy and warmth. It is tantalizing to imagine life there in the deep, perhaps simple microbes, maybe even complex organisms, living out of view in the black waters of an alien ocean. You run a hand over the ice. It's hard as granite at this temperature. Reddish-brown stains near cracks hint at salts or organic compounds brought up from below. Europa is silent, but it holds its secrets close. An ocean under ice, a possible cradle for life adrift in Jupiter's powerful embrace. Beyond Europa orbits Ganymede, largest of the moons. In fact, the largest moon in the entire solar system, even bigger than Mercury. Ganymede appears as a mottled grey-brown sphere with regions of dark ancient terrain and lighter, somewhat younger, grooved regions. It has clearly suffered countless impacts. Its dark areas are saturated with craters. But in the lighter areas, you see long parallel grooves, signs of past tectonic activity that somehow stretched and broke the crust, perhaps from internal upwellings or global expansion. Ganymede is a world of water ice and rock. Its surface is mostly ice, as hard as rock, peppered with craters whose ejecta splashed out bright rays of fresh ice. Like Europa, Ganymede too is believed to hide a subsurface ocean, though deeper below, a thicker crust of ice. And remarkably, Ganymede has its own magnetic field, the only moon known to have one, indicating it likely has a molten iron or iron sulfide core, creating a dynamo like Earth's. As you pass through Ganymede's vicinity, you might feel a slight tug and wobble in Jupiter's magnetic field, evidence of Ganymede's magnetic bubble embedded within the giant planet's magnetosphere. On Ganymede's surface, if you stood there, Jupiter would loom huge in the sky, many dozens of times larger in apparent size than our moon looks from Earth. Its banded face would be visible if the side of Ganymede you're on is facing Jupiter, perhaps with the great red spot discernible as a reddish oval. The sunlight here, 5 times weaker than at Earth, still provides ample daylight on the ice. At night, the sky is dark and full of stars, and Jupiter would be an awesome, softly glowing presence, lighting Ganymede's ground in a dim twilight whenever it hangs above the horizon. Farther out lies Callisto, the most distant of the Galilean moons. Callisto is a world that appears ancient, almost primordial, with a densely cratered crust of ice and rock that seems never to have been reworked by internal forces. Its entire surface is covered in overlapping craters upon craters, so densely packed that new impacts must obliterate old ones. The largest impact basins have concentric rings like ripples frozen in time, Valhalla and Asgard, enormous bullseye patterns from titanic collisions in the far past. Callisto's surface glints with countless tiny bright spots against a darker background. The bright spots are relatively fresh ice exposed by impacts, contrasting with the darker, dustier surrounding terrain that has been weathered by eons of micrometeorite bombardment and radiation from Jupiter. Beneath Callisto's heavily cratered crust, there may also lurk a hidden ocean, according to magnetic data from spacecraft. Even this seemingly inert moon might hold a liquid water layer deep below, sandwiched between ice layers. If so, it is likely heavily mixed with salts and ammonia, and perhaps it never interacts with the surface. Callisto does not exhibit signs of geological activity. It appears to be a relic from the early solar system, its face virtually unchanged for 4 billion years. Drifting above Callisto, you reflect that this moon is like a museum piece, preserving the record of the heavy bombardment epoch in the solar system's youth, unlike its sibling moons which have erased or repainted their surfaces through internal activity. Leaving Callisto, you have sampled the 4 great moons of Jupiter: fire, ice, and 2 shades of twilight between, each distinct, each fascinating. But Jupiter has many more smaller moons too, tiny irregular captured asteroids far out and closer in, a retinue of small inner moons shepherding a thin system of rings. Yes, Jupiter has rings as well, faint, dusty rings, discovered only when spacecraft flew behind the planet and saw sunlight forward scattered. These rings are not like Saturn's broad icy ones. Jupiter's are subtle, made of micrometer dust grains slowly spiraling inward. The dust likely comes from meteoroid impacts on the inner moons like Amalthea and Thebe, each impact kicking up debris that then orbits as a tenuous ring. You might not notice Jupiter's rings unless you catch them at just the right angle with the sun. Still, they form a gentle band of light hugging the planet's equator, a whisper of structure around the gas giant. Turning away from Jupiter, you venture onward. The sunlight now is much fainter than when you began, only a quarter of its intensity at Earth's orbit. Stars crowd the sky as the ambient glare of the sun lessens, but ahead, another jewel awaits: Saturn, Lord of the Rings. Even from afar, Saturn captivates. Its pale golden globe is encircled by a magnificent system of bright, shining rings that span hundreds of thousands of kilometers. As you approach, the rings resolve into countless individual slabs of ice and rock, all orbiting in a flat plane like a celestial vinyl record. Saturn itself is a gas giant slightly smaller than Jupiter, with a more delicate hue. Bands of butterscotch, cream, and grey slide gently around its atmosphere. Its features are more muted than Jupiter's violent contrasts. But Saturn too has storm systems and high-speed winds. A broad, hazy belt girds its equator, and near its north pole you find a strange geometric wonder, the famous hexagon. It is a 6-sided pattern in the cloud tops at the pole, perhaps caused by the peculiar dynamics of a standing wave in the atmosphere. At Saturn's center, unseen below the clouds, lies a smaller core of heavy elements. But like Jupiter, Saturn has no solid surface at its cloud tops. just a gradual transition from gas to fluid. Saturn is less dense than water. In theory, if you had a bathtub big enough, Saturn would float. Yet it is the rings that draw your eye above all. You glide just above the ring plane, skimming the outer edge of the main rings. Stretched out below you is an almost flat expanse of icy particles. Some are grains of dust, others boulders the size of a house. They shine brilliantly in the sun, like countless diamonds on black velvet. The rings are astonishingly thin, in places only tens of meters thick, essentially two-dimensional when seen edge-on, though tens of thousands of kilometers in radial extent. Gently, you dip down into a gap between ring sections. Around you, ice chunks tumble slowly. If you were very quiet, you might even hear the tinkling of tiny impacts as particles collide softly or clump together briefly. Saturn's rings are mostly pure water ice, which is why they gleam so brightly. They likely formed from the breakup of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Now these countless fragments spread out in their orbits, sculpted by gravity into several distinct ring zones, divided by thin gaps. Some gaps, like the Cassini division, are maintained by the gravitational influence of Saturn's moons. Small shepherd moons like Pan and Daphnis carve narrow channels, their gravity herding ring particles and creating sharp edges and waves in the rings. Looking down at Saturn's rings from above is one of the most sublime views in the solar system. You see delicate spiraling density waves, like ripples or grooves in a vinyl record, caused by orbital resonances with moons further out. You see subtle color differences. The B ring is brilliant white, the C ring more dusky and translucent. Sometimes you see fleeting spokes, ghostly radial features that appear and dissipate, perhaps caused by electromagnetic effects, levitating fine particles temporarily above the ring plane. The rings cast a broad shadow on Saturn's cloud tops, a series of dark bands across the planet's face. Conversely, on the night side of Saturn, the rings reflect sunlight and cast a soft illumination, so that Saturn's night side is never completely dark when the rings are in sunlight. Yet for all their glory, Saturn's rings are transient on geological timescales. Already, ring material is slowly raining down onto Saturn, pulled by gravity and dragged by magnetic fields. It's estimated that in another 100 million years or so, the main rings may become thin and eventually vanish, either accreted onto Saturn or dispersed into space. We are lucky to live in an epoch when Saturn wears such magnificent rings. They may be a relatively recent adornment, and one day they will dissipate. But in this moment, as you float among them, they appear timeless and serene, a cosmic masterpiece of natural sculpture. Emerging from the rings, you turn attention to Saturn's family of moons. At least 82 moons circle Saturn, and more continue to be discovered. They range from tiny, irregular chunks a kilometer across to the giant Titan, second largest moon in the solar system. Each moon has its own character. Let us visit a few of the notable ones. First and foremost is Titan. As you approach Titan, you see a hazy orange globe, the only moon in the solar system with a substantial atmosphere. In fact, Titan's atmosphere is thicker than Earth's, made mostly of nitrogen with a touch of methane. It completely hides the surface from visible sight. You descend through this thick orange air, and at around 50 kilometers up, you pass through a layer of methane clouds. A gentle rain of liquid methane might be falling from some of these clouds, not water, which is frozen as hard rock on Titan, but methane, which at Titan's frigid 180 degrees temperature can exist as a liquid. Breaking through the cloud deck, you reach the surface and settle gently onto an open plain near a lake. Yes, Titan has lakes, not of water, but of liquid hydrocarbons. Before you, stretching to the horizon, is a mirror-like expanse of liquid methane and ethane, something like a primordial earthly lake, but under an alien starless sky. The sun here is a feeble yellow point, smothered in haze, so it's a dim twilight at noon. Across the liquid surface, you see the reflection of Saturn's distant glow in the hazy sky above. Though if Saturn is above the horizon, it would only appear as a pale light smudge due to Titan's thick atmosphere. Walking on Titan would be strangely pleasant in some ways. The thick atmosphere and low gravity give it a surface pressure similar to Earth's, and gravity only 1/7 of Earth's. You could actually strap on wings and fly in the dense air if you ran and flapped hard enough. But the temperature is unimaginably cold to us, and you'd need a heated suit to survive, not to mention an oxygen supply. The landscape around you on Titan might look surprisingly familiar in form. You see what appear to be river channels carved into the icy ground, leading to this lake, indeed named Kraken Mare. Rounded pebbles of water ice and solid hydrocarbons lie at your feet, smoothed by flowing liquid. There are even gentle waves on the lake's surface when the wind picks up. At the shore, a sludge of organic rich mud, a bit like wet sand made of plastic, squelches underfoot. Titan's atmosphere, laden with smoggy hydrocarbons created by sunlight-driven chemistry high above, deposits a constant drizzle of complex organics onto the surface. Over millions of years, Titan's surface has accumulated a wealth of carbon-rich compounds, the building blocks of possible biology, waiting perhaps for a spark of life. The air has a hint of aroma if you could smell it through a filter, perhaps a tang of hydrocarbons, akin to gasoline mixed with fainter, sweeter notes from other organics. Titan's world is like a deep-freeze laboratory of prebiotic chemistry, possibly reminiscent of early Earth's chemistry, but at cryogenic temperatures and without liquid water. Mountains of rigid water ice, hard as rock, rise in the distance, softly rounded by the thick atmosphere's lack of erosive power beyond the occasional methane rain. A low sun hangs in the perpetual haze. Daytime is a dusky affair, and as night falls, the clouds and haze block any stars. But occasionally, if the sky clears enough or in certain infrared transparency windows, the majestic presence of Saturn might faintly appear, huge and ghostly, occupying a broad region of Titan's sky, a pale source of light far more subdued than our moonlight back on Earth. Lightning is rare on Titan, as the atmosphere lacks strong convection generally, but who knows? Perhaps a rare thunderstorm could flicker in the distance over one of the hydrocarbon seas, briefly illuminating the alien shoreline. Titan quietly reminds us of Earth in mirror form, an active cycle of liquids, but made of methane. A thick atmosphere, weather, lakes, rivers, maybe even cryovolcanoes that erupt cold mixtures of water and ammonia from Titan's interior. It is a dynamic and complex world all its own, one that could perhaps harbor very strange life that uses liquid methane instead of water. If such life exists, it would metabolize and move in extreme slow motion due to the cold, but it would find Titan a comfortable home. Next, you bid Titan farewell and venture to tiny Enceladus, another of Saturn's remarkable moons. Enceladus is tiny, only about 500 kilometers across, but brilliantly bright. Its surface is fresh, clean ice reflecting almost all the sunlight. As you orbit over Enceladus's southern hemisphere, you witness a breathtaking sight. Multiple geysers of fine icy mist spraying out from long tiger-striped fissures near the South Pole. Enceladus is literally a cosmic fountain. These plumes are composed of water vapor and microscopic ice particles being vented from its interior ocean out into space. The jets feed a large diffuse ring around Saturn, the E-ring, with their ejected material. You fly through a plume. It's unavoidable, as they shoot hundreds of kilometers up. For a brief moment, your spacecraft's windows accumulate a fine frosting as the water vapor hits and freezes. Sampling the vapor would reveal salty water with organic compounds, essentially bits of the subterranean sea of Enceladus. Beneath the surface of this small moon lies a liquid water ocean sandwiched between the rocky core and icy crust, kept warm by tidal flexing from Saturn and perhaps radioactive decay. The plumes erupt through cracks in the ice, likely on the ocean floor. Hydrothermal vents add heat and minerals to the water, which then travels upward and escapes at the cracks. You descend towards one of those long fissures, known as Damascus sulcus, and peer into a bluish trench from which a mist continually emanates. At the edges of the trench, the ground is stained with deposited frost and possibly simple organics from the ocean spray. Surrounding terrain is relatively young, few craters, and marked by curving fractures and ridges. Enceladus's environment is like a natural spa of the solar system. Under its ice, warm water and perhaps life-sustaining chemicals brew and belch out gracefully into space. This moon, tiny as it is, has become one of the prime targets in the search for extraterrestrial life. One can imagine organisms around those hypothesized hydrothermal vents in Enceladus's ocean, feeding on mineral-rich fluids, living in total darkness, but thriving in warmth provided by Saturn's tidal energy. As in Europa's case, we have yet to confirm life, but all ingredients are there. Even in deep space far from the sun, life might find havens where energy and liquid water exist. Enceladus orbits within Saturn's faint E-ring, which it maintains. When sunlight streams through the E-ring at just the right angle, you see a diffuse glitter around Saturn, billions of tiny ice grains catching the light. Some of those grains will eventually fall back onto Enceladus's surface like fresh snow, keeping it bright. Others escape Saturn's gravity or fall into Saturn eventually. In effect, Enceladus is a little icy comet continuously active around Saturn. Another notable moon is Iapetus, which you visit next on your Saturnian tour. Iapetus is half bright ice, half dark as coal. As you approach, you notice its striking two-tone appearance. One hemisphere, the leading face of its orbit, is coated in dark material, making it look like a yin-yang symbol. The other trailing side is bright white ice. Iapetus also has a bizarre equatorial ridge running most of the way around the moon's center, like a walnut seam, making it resemble a piece of a giant shell. This ridge is up to 13 kilometers high in places. No one knows exactly how it formed, perhaps long ago rapid rotation or a collapsed ring that settled on the surface. You pass over a region known as Cassini Regio, the dark hemisphere, and the ground below looks like asphalt sprinkled with frost. Craters on the dark side have bright rime along their rims, where lighter subsurface ice was exposed by impacts. It is a world of stark contrast, quietly circling Saturn at great distance, far beyond Titan. The dark coating is likely a thin layer of organic rich dust, perhaps swept up from outer irregular moons or from Phoebe, an outer moon of Saturn, and deposited on Iapetus's leading face like bugs on a windshield. This deposited material warmed slightly in sunlight and sank into the ice, creating a runaway effect of sublimating the bright ice and leaving behind more dark stuff, thus darkening that side further. Meanwhile, water vapor redeposited on the colder trailing side, making it even brighter. Thus, Iapetus became an extreme study in albedo dichotomy. Time would fail to speak of all Saturn's moons. The tumbling Hyperion, shaped like a sponge, chaotic in its spin, or tiny Mimas, with its huge crater resembling the Death Star, or Enceladus's siblings Tethys, Dione, and Rhea, each with its own pattern of cracks or craters, or ancient rings of frozen impact basins. Saturn's system is a rich archipelago of worlds, each worthy of exploration. But the cosmic clock urges you onward to the next realm beyond Saturn. Past Saturn, the sunlight dims further. The warmth of the inner solar system is far behind. Now you enter the domain of ice giants. First comes Uranus, a pale cyan orb spinning on its side. Indeed, Uranus's axial tilt is about 98 degrees, meaning it essentially rolls around the sun like a ball. When you arrive at Uranus, you find a world that at first seems subdued. Its turquoise atmosphere is almost featureless to the casual glance, just a slight shading from turquoise to deeper teal toward the poles. But careful inspection reveals faint banding and occasional white cloud streaks, likely methane ice clouds high in the atmosphere. Uranus has a faint haze that gives it its uniform appearance. This sideways planet has peculiar seasons. Because it's tipped so extremely, each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness, since one Uranian year is 84 Earth years. Right now, say, it might be that the North Pole is in full sunlight, a bright cap, while the South Pole is in a long dark winter. This tilt might be due to a cataclysmic collision in Uranus's early history that knocked it over. The consequence is extreme but weirdly static seasons. At solstice, one hemisphere bakes, while the other freezes in darkness. However, bake is a relative term here. Even the sunlit pole's atmosphere is frigid, around 200 degrees C, and strangely, Uranus exhibits very little internal heat flow. Unlike its neighbor Neptune or the gas giants, Uranus's interior does not emanate significant extra heat, leaving its atmosphere relatively calm and cold. As you get closer, you notice Uranus is encircled by a set of thin, dark rings. They are much narrower and darker than Saturn's, composed of dark reddish material, likely tholins or radiation-darkened organics on ice. There are about 13 known rings, all quite faint, discovered in 1977 when they occulted a star. They appear as narrow charcoal black hoops around the planet's equator, which is tipped 90 degrees from its orbital plane. So the rings are often seen nearly face-on from the Sun's perspective, alternately showing us their broad face or edge depending on Uranus's position in its orbit. You also spot at least a few small moons embedded among those rings, shepherd moons that keep the ring particles corralled. Uranus has a retinue of at least 27 moons known. The larger ones are intriguing icy worlds themselves: Titania, Oberon, Ariel, Umbriel, and Miranda. Let's briefly visit one or two. Miranda is the smallest of the major moons, but perhaps the strangest. Its surface looks cobbled together from mismatched pieces. Part of it is old, heavily cratered terrain, but then there are bizarre regions that look like no other place, with huge fault canyons up to 20 kilometers deep, chevron patterns of ridges and troughs, and areas that seem almost like they were shattered and reassembled randomly. It's as if Miranda was broken apart by an ancient impact and weakly reformed into a jumbled mosaic. The gravity on Miranda is so low, less than 1% of Earth's, that you could easily hop off a tall cliff and not fear a lethal fall. You would drift down gently. In fact, off Miranda's cliffs, one of which, Verona Rupes, is touted as the tallest known cliff in the solar system, about 20 kilometers high, an object could take many minutes to drop to the bottom. Ariel and Umbriel are mid-sized moons, one bright and one dark. Ariel shows many signs of past geologic activity, a network of valleys and smooth plains that suggest internal ice melted and repaved parts of the surface in the past. Umbriel is darker, an old and shadowed world with many craters and a mysterious bright ring on one crater floor like a frosty deposit. Titania, the largest, shows long canyons and faults too, hinting it was once somewhat active. All these Uranian moons orbit in the planet's equatorial plane, which means they too are flipped on their side relative to the Sun. So at solstice, one hemisphere of each moon is in continuous sunlight, and the other in darkness for years, just like Uranus itself. One can imagine bizarre effects of such prolonged day-night cycles on any potential volatile ices, maybe subtle migration of surface frost from the hot pole to the cold one. The environment out here is hushed and dim. Uranus's magnetosphere rotates on its side, resulting in complex interactions with the solar wind. As you depart the Uranian system, you note the aquamarine planet receding, encircled by its thin black rings and tiny spark moons, a silent, tipped-over world doing its slow roll around the Sun. Pressing farther out, you reach Neptune, the outermost known major planet. Neptune is the twin of Uranus in size and composition. Both are ice giants, with a mix of hydrogen, helium, and a higher proportion of water, ammonia, and methane ices in their interiors. But Neptune has a much more dynamic personality. As you approach Neptune, you see a rich azure blue planet with a few obvious features. There is a dark oval storm system reminiscent of Jupiter's red spot, the Great Dark Spot, though by now it might have dissipated since it was last seen by Voyager 2 in 1989. Neptune's dark spots come and go. You also see high-altitude bright white clouds, likely methane ice cirrus, casting shadows on layers below as they race around in Neptune's fierce winds. Indeed, Neptune holds the record for the fastest atmospheric winds in the solar system, with jet streams up to 2,000 km/h. How such ferocious winds arise on a planet receiving so little solar energy is still somewhat mysterious, but Neptune does radiate more internal heat than Uranus, fueling more weather. At Neptune's south pole, the one Voyager saw sunlit, a haze of orange smog was observed, perhaps some warming effect creating slight color change. Neptune too is tilted, about 28 degrees, similar to Earth's 23 degrees. So it has seasons, though each season lasts over 40 years given its 165-year orbit. Currently, perhaps the southern hemisphere is transitioning to darkness and the north coming into light. Observations from Earth's telescopes in recent years have shown that Neptune's clouds and storm activity wax and wane with seasons. For instance, more frequent dark spots and bright clouds at certain times. Like all gas ice giants, Neptune has rings as well. Neptune's rings are faint and reddish, and not uniform. Intriguingly, they have clumpy segments called ring arcs, particularly in the outermost Adam's ring. These arcs, named Liberté, Égalité, Fraternité, and Courage, puzzled astronomers because orbital mechanics say a continuous ring should spread out evenly, yet here, material clumps in certain sections. It's now thought that one of Neptune's moons, Galatea, herds these arcs gravitationally and keeps them from dispersing. Neptune has a retinue of moons, 14 known. The standout is Triton, one of the most fascinating moons in the solar system. When you arrive at Triton, Neptune's largest moon, you are met with an icy pinkish landscape. Triton orbits Neptune in a direction opposite to Neptune's rotation, a retrograde orbit, strongly suggesting it was a captured Kuiper Belt object rather than forming alongside Neptune. Because of this, Neptune's gravity is gradually pulling Triton inward. In some distant future, billions of years, Triton will either break apart into a ring or crash into Neptune. But not yet. Triton's surface is extremely cold, about 235 degrees Celsius, cold enough that nitrogen exists as frost and methane, and carbon monoxide ices decorate the surface. Voyager 2's flyby revealed Triton's surface to be surprisingly complex and young in places. Large swaths of terrain with few craters, indicative of recent reshaping. At Triton's south polar region, a cap of faint pinkish nitrogen ice and methane ice lay with dark streaks across it. Those streaks, it turned out, were the fallout from geysers. Yes, Triton too has active geysers. When sunlight in the southern spring warmed transparent layers of frozen nitrogen, it likely caused sublimation and pressure buildup beneath, eventually erupting as geysers of nitrogen gas, carrying dark dust up to 8 kilometers high. The gas then blew downwind, depositing the dust in dark plumes that extended many tens of kilometers. You might witness one of these right now. Imagine standing on Triton's endless plain dubbed the cantaloupe terrain, because its texture looks like a cantaloupe rind, likely due to diapirs or rising blobs of ice causing the surface to deform. In the distance, a whisper-quiet geyser begins. An invisible jet of nitrogen gas lofts, a column of fine, dark particles. Because Triton's atmosphere is extremely tenuous, only a fraction of a pascal of pressure, you cannot hear anything, but you see a faint, hazy plume rising and drifting sideways ever so slowly. The sky is a pale peach near the horizon from the thin haze, and above it quickly darkens to black. The sun is weak, barely providing any heat. You can feel the deep cold even in your insulated suit. Triton's terrain has variety. The Cantaloupe region, the polar caps, and weird zones of what look like melted terrain, possible cryovolcanic landscapes where slush may have erupted in the past and refrozen into smooth plains. You move over a region called Leviathan Patera, an irregular walled depression that could be a collapsed caldera of an ice volcano. Near the terminator line, where day meets night, you notice the glint of starlight on what appears to be smooth, reflective surfaces. Could these be lakes of liquid nitrogen? Possibly not stable, but maybe transient pools when seasonal heating allows some melting of the nitrogen ice. Neptune's other moons are far smaller. Nereid, Proteus, a large, irregular dark chunk, heavily cratered, that Voyager imaged, nearly filling its Roche limit around Neptune but stable, and several newly discovered tiny ones. But none approach the interest of Triton. Now you have traversed all 8 major planets from the bright furnace of the Sun's vicinity to the twilight realm of Neptune. Beyond Neptune, the formal boundary of the classical solar system, there lies the vast expanse of the Kuiper Belt. Once, Pluto was considered the 9th planet, but we now know it as one of the largest members of this belt of icy bodies at the fringe of the Sun's influence. Your journey continues outward, and soon you encounter Pluto, shimmering dimly with a faint beige-white color mottled with darker patches. Pluto is a small world, only about 2/3 the size of our moon, but it is rich in character. As you draw near, you see an enormous bright heart-shaped feature dominating one hemisphere. This heart is Tombor Regio, and its western lobe is a vast basin of nitrogen ice called Sputnik Planitia. This frozen plain is unlike anything you've seen. It's a smooth, cream-colored expanse with subtle cellular patterns on it. Those cells are outlines of convection within the nitrogen ice. Yes, the frozen nitrogen here, soft as wax, is slowly churning over eons, like a gigantic lava lamp of frost. This convection constantly renews the surface, erasing craters, so Sputnik Planitia is essentially craterless and very young in appearance. You skim low over it and realize you're flying above a frozen sea of molecular nitrogen. In places, you see pits where nitrogen has sublimed away. In others, where perhaps a recent impact delivered a jolt of heat, the nitrogen might have melted and refrozen. At the edges of the heart-shaped plain, you find towering water ice mountains named Hilary Montes and Norgay Montes. Some peaks reaching 4 to 5 kilometers high, thrusting jaggedly above the plains. Water ice on Pluto is as strong as rock and forms the bedrock that the softer ices, nitrogen, methane, carbon monoxide, overlay. These mountains may be uplifted blocks of water ice or the rims of an ancient impact basin, now filled by Sputnik's ice. North of the heart lies a rugged highland of older ice, cut by canyons and dotted with crater depressions. To the east, a vast region of reddish-brown hues called Tartarus Dorsa is covered in strange aligned ridges like scales or bark. They call them bladed terrain, likely huge sublimation sculpted cliffs of methane ice. Perhaps where volatile ices have preferentially vanished, leaving behind the harder stuff in blade-like formations oriented by sun exposure and wind. On the dark anti-heart side of Pluto lies a large, diffuse, dark region called Cthulhu Macula, a possibly organic rich expanse, older and heavily cratered in spots, with a draping of dark tholin, complex organic molecules created by UV light acting on methane, giving it a ruddy charcoal color. Sunset on Pluto comes swiftly. The sun is just a brilliant star here, providing twilight-level illumination even at noon. As darkness falls, the sky reveals something wondrous, a soft blue haze around Pluto, surprising for such a small world. This haze is made of layered photochemical smog. Sunlight, even weak, triggers chemical reactions in the thin atmosphere, converting methane into complex hydrocarbons, which then condense into tiny particles, creating a delicate multi-layered haze up to 200 kilometers high. The haze is visible when the sun is low, scattering blue light, giving Pluto's limb a cerulean halo. Through that haze, you might see the pinprick of the sun setting and also another pinpoint shining. That would be Charon, Pluto's largest moon. Charon is half the diameter of Pluto, so big compared to Pluto that the two orbit each other around a point in space between them. One could call Pluto-Charon a double dwarf planet system. They are tidally locked to each other, always showing the same face to one another as they twirl in a 6.4-day dance. You decide to pay Charon a visit, drifting across the 20,000-kilometer gap separating them. Charon is grayish, with a dark reddish polar cap. A cap that likely comes from gases escaping Pluto and getting trapped and frozen onto Charon's pole during winter, where radiation then chemically alters them into red tholins. Charon's surface shows an expansive system of chasms, a giant belt of fractures that wraps around, indicating that at some point, Charon's interior water may have frozen and expanded, cracking the crust. There is a prominent large crater with bright rays near the equator, called Arakoth, impact by some, though unofficial, which hints that beneath any weathering, Charon's water ice is relatively clean and bright when excavated. On the far side of Charon, which we did not see via spacecraft, presumably more craters dominate. Charon has no atmosphere to speak of, so its surface is static and dead-looking, but still fascinating as a record of what goes on at the solar system's edge. Looking back at Pluto from Charon, you see Pluto's hazy silhouette occulting the distant sun, and a ring of light around Pluto's limb, an atmosphere and haze backlit, glowing a faint gold and blue. This reminds you that even these tiny worlds have complexity and beauty. Pluto's atmosphere is extremely thin, about 100,000 times thinner than Earth's at surface. Mainly nitrogen with some methane, but it is escaping gradually as Pluto can't hold it forever. In Pluto's sky during day, that atmosphere would likely produce a blue tint, and one could even see a faint sunbeam or twilight after sunset due to the haze. Departing Pluto and Charon, you now sail truly into the unknown dark. The sun becomes just one star among many, albeit the brightest. You have entered the Kuiper Belt fully. Here exists a vast collection of icy bodies, leftover planetesimals from the solar system's formation, preserved in cold storage. Many of these are small, irregular chunks, only a few kilometers wide, but some are quite large, Pluto's size and bigger. In fact, not far beyond Pluto in a cosmic sense lies Eris, a dwarf planet slightly smaller than Pluto, but more massive, with an even higher density, suggesting less ice fraction. Eris is so far from the Sun that its atmosphere, if it has one, is entirely frozen onto its surface most of the time. When nearer perihelion, perhaps a thin layer of atmosphere sublimates. Now at aphelion, likely it's frozen solid. Eris's surface is extremely reflective, perhaps from a coating of nitrogen or methane ice, making it one of the brightest objects in the Kuiper Belt. There are also Haumea, an elongated, rapidly spinning dwarf planet with a weird shape and a family of collisional fragments trailing it. Makemake, another bright reddish dwarf planet slightly smaller than Pluto, and numerous others being discovered each year. The Kuiper Belt extends from about 30 AU, Neptune's orbit, out to roughly 50 AU in a broad torus around the Sun's ecliptic plane. The population here moves in leisurely orbits around the Sun, taking hundreds of years to complete one circuit. Occasionally, gravitational nudges, perhaps from Neptune's past migration outward, have scattered some objects into eccentric or inclined orbits. Some cross Neptune's path, like Pluto, a resonant KBO locked in 3-2 resonance with Neptune. Others have been flung into even more distant orbits. As you continue outward, you pass countless unseen worlds. One such world presents itself in your path, a contact binary shaped like two lumpy spheres stuck together, resembling a snowman. This is similar to Arakoth, which New Horizons visited in 2019, likely a primordial object that formed by the gentle merger of two separate bodies. Its surface is very red from organic compounds, and it has no craters or geologic activity. It's a frozen time capsule from the birth of the planets. Such objects abound out here. Now the Kuiper Belt's outer edge appears. The density of large bodies thins out beyond about 50 AU. You are entering now the deep freeze, the realm of the comets. Out here, the sun is but one of billions of stars in the sky, and the warmth and light are feeble. This is the beginning of the Oort cloud, though at first perhaps better to say the scattered disk, a transitional region with objects on very elliptical or inclined orbits, which sometimes bring them far out, hundreds of AU, before returning toward the sun. You might pass one such traveler, perhaps a comet nucleus quietly drifting at aphelion, building up a dark crust of complex organics as cosmic rays process its ices over eons. At this distance, it is just an inert black potato a few kilometers across, waiting until one day a stellar perturbation or gravitational resonance nudges it onto a trajectory inward, where it will sprout a glowing coma and tail and be reborn as a comet blazing in the inner solar system's skies. But beyond even these distant scattered objects lies the true boundary of the sun's kingdom, the Oort cloud. It is not a flat belt, but a vast spherical swarm of countless icy bodies surrounding the solar system in all directions. A shell of potential comets extending perhaps as far as 100,000 AU, nearly 1.5 light-years, from the sun. This region is mostly empty space, with objects tens of millions of kilometers apart, but within it reside perhaps trillions of comets. These are ancient leftovers from the formation of the outer planets that were flung out here by gravitational interactions long ago, or they are outer solar nebula condensations that never coalesced into larger bodies. Here, the sun's gravity is so weak that passing stars, or even tides from the Milky Way's mass distribution, can perturb or dislodge these comets. You find yourself floating in the darkness between stars. The sun is a very bright star behind you, but no longer overwhelmingly so. You can even look straight at it without shielding now, as it's barely brighter than Venus as seen from Earth, just a point of intense light. Out here, in the silence and darkness between the stars, as a NASA text once described the Oort cloud, you have reached the threshold of interstellar space. The icy nuclei of comets drift like sleepy moths around a porchlight, as one poetically put it, the porchlight being the distant sun, now just one star among many. Pick one such Oort cloud object, say, an untouched comet nucleus named perhaps after some catalogue number. It is an irregular body a kilometer or two wide, surface pitch black with some reflectivity, maybe only a few percent. It might have a crust of tar-like organics covering a matrix of ice and dust inside. It has been in deep freeze for 4.5 billion years, nearly unchanged since the time it formed close to the sun, before being ejected to the fringe. Occasionally, over the millennia, a passing star's gentle tug perturbs its orbit slightly. Most times, it remains bound to the sun, but sometimes, rarely, such nudges send an Oort cloud body falling inward as a long-period comet. Perhaps one day, this particular one will do so and delight future skywatchers with a bright tail. At the moment, however, here at roughly 30,000 AU from the sun, you are effectively beyond the heliosphere. In fact, you likely pass the heliopause, where the solar wind's influence yields to the pressure of the interstellar medium, back around 120 AU, a tiny fraction of the distance to the Oort cloud's far edge. That boundary is where Voyager 1 and 2 transitioned into true interstellar space in recent years. Now you are well beyond that, immersed in the sparse interstellar gas of our galaxy. Charged particles from the sun no longer dominate. Instead, cosmic rays, high-energy particles from distant stellar events, roam freely. Magnetic fields from the galaxy thread through space, only slightly perturbed by the sun's faraway presence. As you drift still outward, even the Oort cloud becomes tenuous. Eventually, at around perhaps 100,000 to 200,000 AU, about 2 to 3 light-years, the sun's gravitational grip on comets is at its limits. You are now truly in between the stars. It is dark. Dark beyond any night you experience near Earth, because here no nearby sun lights any sky. Yet, it is not pitch black. Look around. The Milky Way galaxy is a glorious band across the sky, far richer and brighter than from Earth because there is no atmosphere or light pollution. You see the combined glow of billions of distant stars in that band. You also see many individual stars too, brilliant blue-white ones, closer yellow ones, distant red ones. One of those stars, shining with a steady golden light behind you, is the sun as seen from here. Surrounding it, if you squint, you might just detect a very faint spherical cloud of comets reflecting its light weakly. The sun's aura of Oort cloud. Take a moment in this deep space to consider scale. It took light about a year to travel from the sun to your current position. The nearest star to the sun, Proxima Centauri, is still about 3 light-years further on. The emptiness is profound, but not absolute. There are wisps of interstellar gas and dust. You might encounter a diffuse molecular cloud, a region with slightly higher density of hydrogen molecules and dust, perhaps the birthplace of future stars. Out here, as you cross into the domain of the galaxy, you can almost feel the transition. Your spacecraft's instruments detect a change in the charged particle population. Galactic cosmic rays are the main contributor now. You are now in the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between stars and makes up much of the volume of the galaxy. If your eyes could see in radio or other wavelengths, you might notice the subtle glow of the cosmic microwave background in all directions, or emissions from distant nebula. But visually, it's the stars and the dark that command attention. Now your perspective begins to widen. With the sun now just another star behind you, you turn your gaze to the Milky Way as a whole. Imagine rising above the plane of the galaxy, which requires magical rapid travel on your part, beyond realistic speeds. But in this thought journey, you can transcend such limits at will. As you gain a bird's-eye view of our galaxy, its structure emerges. A majestic spiral disk with arcing arms of starlight and dark ribbons of dust. The sun resides in a minor spur between major arms, about 27,000 light-years from the galactic center. From above, you locate the sun's position, not marked by anything obvious, just one G-type star among billions, currently in a small local arm segment called the Orion Arm or Orion Spur that connects the Sagittarius and Perseus arms. If you mark it mentally, you can trace the sun's slow orbit around the galactic center, one circuit every 230 million years or so. The galaxy's disk is a flat glowing storm of stars, gas, and dust, roughly 100,000 light-years across. The central region is a swollen bulge of older yellowish stars, within which lies the very hub, a mysterious bright radio source known as Sagittarius A, which is the location of a supermassive black hole around 4 million times the mass of our sun. You cannot see the black hole directly, unless you have radio or X-ray eyes, but you see the effects. Stars orbiting a seemingly empty point at incredible speeds, and sometimes flares of high-energy radiation as material gets accelerated and swallowed. The center is ringed by a torus of gas and possibly peppered with X-ray binaries and exotic objects near the black hole. If you were to venture there, you would find space severely curved by gravity and the density of stars unbelievably high, a chaotic, energetic environment. Radiating outward from the central bulge are the spiral arms. These arms are not physical arms, like solid appendages, but rather regions of higher density that propagate through the disk, triggering star formation in their wake. As you look at the Milky Way's face, you identify the major arms. The Perseus arm is prominent, sweeping along the outer part of the galaxy. The Scutum Centaurus arm, which passes nearer the center and out. Perhaps two main symmetric arms in a grand design spiral pattern, and some spurs and feathering branches aside, like the Orion spur where the sun is. In the arms, you see blue patches and pink knots. These are hot young stars and glowing nebulae respectively. Giant molecular clouds in the arms collapse to form new stars, and those newborns, massive hot O and B stars, illuminate the surrounding clouds, H2 regions glowing pink with ionized hydrogen, and shape them with stellar winds. The blue star clusters shine strongly, but briefly before their stars die in supernovae. Indeed, scattered throughout the arms, you also see the remnants of past stellar death, supernova remnants, expanding shells of gas like the Crab Nebula or Vela, emitting tendrils of enriched material back into the interstellar medium. These events seeded heavier elements, carbon, iron, etc., into the galaxy, the very elements that later incorporated into new stars and planets, and into you and me. Between the arms and swirling around, an ethereal mist of diffuse interstellar gas persists. Dark patches in the galactic disk silhouette against the starry backdrop. These are enormous dust clouds blocking visible light. One famous such dust lane splits the Milky Way as seen from Earth, the Great Rift, caused by clouds in the inner arms. But from above, you just see them as dark swathes in the disk. If you had infrared vision, however, the dust becomes more transparent and you see even more myriad stars hidden behind. The whole galaxy rotates. The stars in the disk orbit the center in roughly the same direction. But intriguingly, the rotation curve, how orbital velocity changes with distance, is flat. Stars far out orbit just as fast as those closer in, defying the expectation if only visible matter existed. This was one key clue for the existence of dark matter, an unseen mass component enveloping galaxies. So though you do not see it, you know that the Milky Way is embedded in a vast halo of dark matter, extending well beyond the visible disk and containing perhaps 5 times more mass than all the stars and gas combined. This dark matter neither emits nor absorbs light. It interacts only gravitationally, and perhaps through some other weak forces yet unknown, but it provides the gravitational scaffold that holds the galaxy together and the cosmic web beyond. Beyond the disk and bulge, you find the stellar halo, a sparse spherical distribution of ancient stars and globular clusters. Globular clusters, as you see, are compact spheres of tens of thousands of very old stars orbiting the galaxy in all directions. They appear as glittering dense balls, mostly toward the galactic bulge, but also some far out. These are fossils of the early galaxy formation, essentially. The halo stars and clusters often have very low heavy element content, metallicity, indicating they formed before previous generations of stars had seeded the environment with heavy elements. There are about 150 known globular clusters swarming around the Milky Way, each like a beehive of stars, perhaps 12 to 13 billion years old. Their orbits take them plunging through the disk and out again, oriented randomly. Our vantage now drifts further outward, and the whole Milky Way appears smaller. You note it is a barred spiral galaxy. The central bulge has a bar structure, a stretched nucleus of stars, from whose ends the spiral arms likely emanate. Indeed, surveys of stars at the center show an elongated bar shape. Such bars are common in spiral galaxies and can drive gas inward, perhaps helping fuel star formation or feed the central black hole. The Milky Way's bar is subtle to our eyes, but distinct in infrared studies. Encircling the Milky Way is also a tenuous halo of hot gas, observed via X-ray emission, and even the remnants of past devoured galaxies, streams of stars that were torn from dwarf galaxies that ventured too close, now wrapping around the galaxy in giant loops. Now your mind's eye travels even further out, such that the entire Milky Way is seen as a small spiral among others. The night sky as we know it with constellations is but one perspective from within. From out here, those constellation patterns disappear as you see the true 3D arrangement of stars. The Milky Way appears about 100,000 light-years in diameter, with the disk perhaps only 1,000 light-years thick. It contains perhaps 200 to 400 billion stars, hard to count precisely, plus interstellar gas equal to maybe 10 to 15% of the total luminous mass, and that central black hole. Now you begin to perceive that the Milky Way is not alone. It is part of a small cluster of galaxies we call the local group. The nearest big companion is the Andromeda Galaxy, M31, a spiral slightly larger than the Milky Way, about 2.5 million light-years away. You turn your view toward it, a grand spiral with perhaps 1 trillion stars. Even from Earth, it's visible as a smudge in dark skies. From this omniscient vantage, you see its spiral arms and dust lanes clearly. It too has satellite galaxies. In fact, as you look between the Milky Way and Andromeda, you notice many small elliptical fuzzballs and irregular fragments. These are dwarf galaxies bound in the local group. The Milky Way alone has dozens of known dwarf satellites. The large and small Magellanic Clouds are the most luminous, visible as cloudy patches in the southern Earth sky, but also fainter ones like Sagittarius Dwarf, currently being tidally disrupted, Draco, Ursa Minor, Sculptor, Fornax dwarfs, and many ultra-faint dwarfs discovered in recent surveys. Andromeda has its own entourage of dwarfs. The third largest member of the local group is the Triangulum Galaxy, M33, a graceful smaller spiral orbiting perhaps around Andromeda. As gravity dictates, Andromeda and the Milky Way are actually moving toward each other. In about 4 billion years, they will begin to collide and merge, dancing a gravitational waltz that will fling stars into new orbits and trigger cascades of starbirth as gas clouds slam together. Eventually, they will likely form a single elliptical galaxy, sometimes nicknamed Milkomeda. But for now, they are distinct island universes, drifting closer in the cosmic ocean. Our local group is falling toward a larger structure, the Virgo cluster, a massive cluster of galaxies about 50 to 60 million light-years away, containing thousands of galaxies. Indeed, step back further, and you behold that galaxies collect into clusters and superclusters along filaments, with great voids in between, the cosmic web. The local group and the Virgo cluster, and others, are part of the Virgo supercluster, or local supercluster, although modern understanding defines an even larger entity called Laniakea supercluster, which includes Virgo and other clusters, all gravitationally moving together. At this truly grand scale, a few 100 million light-years across, the pattern of the universe emerges clearly, like a sponge or foam, where galaxies are concentrated along filaments and sheets surrounding vast, empty voids. It's as though the large-scale structure has a web-like or honeycomb pattern. This is the cosmic web, the result of initial tiny density fluctuations in the early universe that grew under gravity into the complex structure of clusters and voids. The nodes of the web are rich clusters of galaxies, like Virgo, connected by filaments, lines of galaxies and groups, and between them lie voids 100 million light-years across with very few galaxies. One might wonder, why this filamentary structure? Cosmological simulations and observations tell us it's due largely to dark matter scaffolding. Dark matter clumped first, forming a web-like structure under gravity, with voids where there was slightly less matter initially. Normal matter fell into those gravitational wells, forming gas clouds that became galaxies at the nodes and along filaments. Over billions of years, gravity steadily draws matter into this web, making clusters grow by accreting smaller groups and the filaments draining into clusters. Our local group is on an outskirt of the Virgo cluster, likely slowly being pulled toward it. At these scales, you also become aware of the mysterious presence of dark energy, an even more enigmatic component of the universe. About 70% of the total energy content of the universe appears to be in this form. It does not cluster like matter. It is uniform, permeating all of space, causing space itself to expand at an accelerating rate. Whereas gravity, from matter, works to slow expansion and pull things together, dark energy pushes space to expand faster. About 6 billion years ago, dark energy's effect became dominant over matter's self-gravity, and since then the expansion of the universe has been speeding up. Thus, while a localized cluster like Virgo can overcome expansion due to its own gravity binding it, distant clusters are receding from each other at ever-increasing speeds. Now, imagine time as well. You look far enough out in space. You also look back in time, because light takes time to reach you. So at the largest scales, you can see glimpses of the early universe. For example, the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, comes from all directions. From a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and became transparent. It's a faint glow primarily in microwaves now, due to the redshift from the expansion, but it shows tiny temperature fluctuations, the seeds of the future galaxies and clusters. That is the ultimate horizon of the observable universe for electromagnetic waves. Beyond that, the universe was opaque plasma, but neutrinos or gravitational waves can give hints from even earlier. Your journey of the mind now spans 13.8 billion years of history and tens of billions of light years of space. You witness how from a nearly uniform hot plasma, the cosmos expanded and cooled, forming hydrogen and helium gas, which coalesced into the first stars and galaxies a few 100 million years later. Those first stars, population 3 stars, were massive and short-lived, exploding as supernovae that enriched the cosmos with heavier elements. Galaxies formed and merged and grew. In the centers of many, massive black holes formed early and grew by accreting matter, sometimes shining as quasars that outshone entire galaxies with their brilliance. You could see in extremely distant galaxies, thus, early in time, these quasars and proto-galaxies flickering in the cosmic dawn. Over billions of years, galaxies matured into the shapes we see today. Some became ellipticals, often from mergers of spirals. Others remained spirals. Dwarf galaxies aplenty swarmed around bigger ones or drifted lonely in voids. Clusters assembled. Bubble-like voids grew as matter flowed into structures. Now consider that all the while, through the vastness of space and time, the atoms that now make up your body were forged in this cosmic process. The hydrogen in your cells likely formed minutes after the Big Bang. The carbon, oxygen, nitrogen in your body were synthesized in the core of a star that lived and died before our sun was born. The iron in your blood, the calcium in your bones, those came from the violent explosion of a supernova scattering its enriched guts into space. That dust and gas then coalesced 4.6 billion years ago in a swirling disk around the young sun to form Earth and all life's ingredients. The water you drink likely contains hydrogen from the beginning of time and oxygen from long-dead stars, combined on Earth perhaps by chemical processes involving those same elements. Eventually, perhaps inevitably, from this mix of elements on Earth, life emerged, and eventually that life evolved to conscious beings able to ponder their origins. We are such stuff as the stars made, literally stardust brought to life. The space out there is not just black void, it is the matrix from which everything came. From this grand perspective, slowly you make your way back home. Zooming in from intergalactic space, you find the local group, the Milky Way, one of its spiral arms, the Sun, and our pale blue Earth circling it. You see Earth anew, a bright blue oasis amid the darkness, its white clouds swirling in an active dance, its polar caps gleaming, its green-brown continents showing hints of forests and deserts. Sliding down through Earth's comforting atmosphere, you return to where you began, sunlight warming human skin, wind rustling through leaves. Perhaps it's sunrise now. The sun peeks over the horizon, lighting dewdrops on grass into tiny rainbow sparkles. You feel the gentle warmth again on your face. Only now you carry the awareness that this warmth has an ancient, epic journey. From the core of our star where it was born, across the vacuum of space, touching worlds on the way, reflecting off moon and rings, until finally it caressed your cheek. You open your eyes. Above, the morning sky is blue and quiet. The same sun whose fires we skimmed now lights up the clouds in shades of pink and gold. The same earth where life flourishes now lies beneath your feet, solid and nurturing. You realize something profound. The line between us and space is an illusion of perspective. The air you breathe was assembled from atoms gathered across the galaxy. The heat in your body is the stored energy of the sun's rays, captured by plants and passed as food to you. The calcium in your bones was forged in a star's supernova ash. The very concepts of today and yesterday make no sense without the cosmic cycles of Earth's rotation and orbit. You are not separate from the universe. You are a part of its exquisite, ongoing story. In this moment of stillness, standing on Earth under the sun's glow, you can feel the unity of it all. The solidity of the ground, the cool whisper of the breeze, the distant glitter of stars that will appear by evening. It's all connected. The space that seems so remote is in fact within you, around you, of you. When you gaze at the night sky, you are looking into your own cosmic past. When you feel the sun's warmth, you are touching a nuclear furnace 150 million kilometers away that gives life to our world. When you drink water, you consume molecules that likely migrated through cometary ice and Earth's primordial oceans over eons. Returning to that gentle, contemplative breath you began with, you understand now that space is not a distant void separate from human existence. It flows through everything. The atoms in your body were scattered across space before coming together here and now. The gravity of the Earth that holds you is the same force that shapes the orbits of planets and the dance of galaxies. The light that lets you see has traveled years or minutes or seconds through space to reach your eyes. As the day progresses, you carry this awareness with calm wonder. Our planet Earth, with all its busy life, is embedded in the vast cosmos like a small bright fleck in a great ocean. But we are not adrift or isolated. We are profoundly connected to that ocean. We are made of it. The boundary of atmosphere and space is no boundary at all, merely a gradual thinning of the air. Space is already here. It begins a few dozen kilometers above us and extends outward indefinitely. Earth floats in it, and space even permeates the atoms within us, mostly empty space inside atoms too. The journey outward and back has etched into you a quiet understanding. The universe is not a separate place you visit. It is home. From the sun's warm light on your skin to the elements in your blood, from the moon's pull on the tides to the spark of thought in your brain, powered by chemical energy that ultimately traces back to the sun, you are a miniature universe within the universe, a conscious fragment of the cosmos contemplating itself. Above, the sky has turned a deep daytime blue. Somewhere beyond that blue, planets are orbiting, stars are burning, the galaxy is rotating, and the universe is expanding, all in majestic silence and scale. But here, right now, you feel no disconnect from those faraway happenings. They led inexorably to this moment. And in every moment going forward, the atoms that compose you will someday return to the Earth, perhaps become part of new life, and eventually return to space when Earth itself is engulfed by the sun's red giant phase long in the future. Even that is not an end, but a transformation. Maybe some of our atoms will float in a planetary nebula, or be part of the sun's remnant white dwarf, or get incorporated into a new star system. Space is not cold nothingness. It is the cradle of everything that is. It is the gentle night that holds all our days. It is the canvas on which the galaxies paint their histories, and on which each of our lives is drawn as well. Feeling this unity, you stand quietly as the sun climbs a bit higher, spreading golden light over the waking world. In the morning air, you inhale deeply. The breath fills your lungs, and you realize it contains argon atoms exhaled by dinosaurs perhaps, and before them by amphibians crawling out of ancient seas, and before them by bacteria in primordial mats, and now by you. Eventually, those argon atoms, chemically inert, will still be part of Earth's atmosphere when the sun leaves the main sequence. A soft smile forms. You see that nothing is ever truly lost in the universe. It only changes form. The energy that was in the core of a star now powers the beating of your heart. The soul, if you will, of every person is built of the soul of the cosmos. From the sun's serene rising to the stars that will sprinkle the dusk, from the ground underfoot to the faint nebulae in telescopes, it is all one continuous story, one breath, one orbit, one unfolding miracle. The space that surrounds us is also within us. We are the universe, and the universe is us. Space is not separate from us. It is us. Night after night, for billions of years, they have watched from the darkness. Moons, those pale, silent companions, have hung in the sky over every epoch of Earth's history. Long before any human drew breath, our moon cast its gentle light and stark shadows across primordial oceans and nascent continents. It lit the way for the first creatures that crawled onto land under its silvery glow. It has been a witness to all of our story. Imagine a night 100 million years ago, when the moon's pale disk shone down on primeval forests and the backs of dinosaurs. Those ancient giants cast shadows by lunar light among the ferns, unaware that the same moon would later glow upon early humans building fires on the savannah. The moon looked down on all of them, unchanged as ages passed. Through extinctions and renewals, through the drift of continents and the rise of consciousness, it kept hanging in the sky. By the time our species arrived, the moon was a familiar beacon overhead. It saw every ritual dance in its honor, every lover's whisper under its radiance, every explorer who dared to reach for it. In the stillness of midnight, the moon looms as a quiet guardian. Its face, scarred by ancient craters, glows with a cold fire, illuminating the night, but never speaking a word. Yet in its silence, it has shaped the rhythms of life. The tides rise and fall to its tug, a planetary heartbeat set to the moon's pulse. In its waxing and waning, humans have seen a mirror of time's cycles, growth and decay, birth and rebirth. Its cool light has guided travelers, stirred the imagination of poets, and provoked the curiosity of scientists. It is our closest celestial neighbor, and for much of human existence, it was the most mysterious object we knew. But the moon in our sky is not alone in the cosmos. It is one of dozens of such natural satellites in our solar system, and countless more in others, each with its own story. They are as varied as the worlds they orbit. Some shine with icy shells, some seethe with volcanic fury, some hide oceans beneath their crusts, and some are mere shards of rock tumbling in irregular paths. They are the silent watchers not just of Earth, but of every planet they accompany, casting light and shadow across the history of the solar system. This documentary journey is an odyssey across time and space, an immersion into the world of moons. We will trace the arc of their narrative, from the ancient myths woven about our moon to the bold exploration of distant moons by spacecraft, from the violent cosmic dances that birthed them to the subtle gravitational embraces that guide their motions. We will stand on the cratered shores of our moon and feel how it shaped Earth's destiny. We will voyage outward to witness fiery Io, icy Europa, and enigmatic Titan. We will delve beneath alien ice looking for the stirrings of life and soar alongside spacecraft as they reveal these new frontiers. Through poetic reflection and scientific insight, we will see moons not as mere rocks circling planets, but as dynamic characters in the grand story of the cosmos. These are worlds that orbit something greater, yet each is a world unto itself. They teach us about creation and chaos, stability and change, and perhaps even about ourselves. Let us begin under the moonlight that has bathed our planet since time immemorial. Let us listen to the silence of the moon and imagine the tales it could tell of Earth's earliest days, of the creatures that evolved under its glow, of the humans who gazed up and found meaning in its face. The story of moons is the story of companionship in the heavens, of smaller worlds bound to larger ones, influencing and illuminating each other in an eternal cosmic dance. And as we explore these stories, we may find that their light guides us not just across the night, but toward understanding our place in the universe. Ancient eyes and mythic tales. Before the age of science, the moon was a canvas for human imagination. In the deep nights of prehistory, our ancestors looked up with wonder and wove stories to explain the glowing disk that waxed and waned overhead. To them, the moon was more than a rock in the sky. It was a deity, a guide, a timekeeper. Each culture filled the lunar silence with its own voice. Imagine a campfire tens of thousands of years ago, flickering beneath a full moon. A storyteller gestures at the bright orb and recounts how it came to be. Perhaps it is a celestial huntress riding a silver chariot across the sky, as the ancient Greeks believed when they personified the moon as Selene, her face aglow in nightly vigil. Or picture the people of ancient China celebrating the autumn full moon with lanterns and mooncakes, telling of Chang'e, the woman who flew to the moon and lives there forever with her jade rabbit companion. In the myths of the Maya, the moon could be a goddess like Ishel, pouring her light down as a blessing on crops and people. Across the world, countless legends cast the moon as a powerful presence, sometimes male, often female, always influential. These myths carry deeper truths about the moon's importance. Early peoples noticed that the moon's cycle of phases matched the rhythms of nature. The word month itself comes from the moon's cycle, and many ancient calendars were built on its changing face. With roughly 29 days between full moons, the lunar cycle offered a natural unit for measuring time. Under the steady beat of those cycles, humans learned to predict the coming of seasons and tides. The moon became a clock in the sky. In coastal communities, the link between the moon and the ocean's tides was observed and ingrained in law. Fishermen timed their outings by the phase of the moon, knowing the waters responded to its pull. Farmers planted and harvested by planting moons and harvest moons, guided by lunar light and timing. The moon also became a beacon for navigators and travelers. Before artificial lights, its glow on a clear night could illuminate paths and reflect off rivers to guide boats. It's no wonder that full moons inspired gatherings and celebrations. The bright nights were a gift from the sky. In various languages and traditions, each full moon had a name reflecting the seasonal law: the wolf moon of deep winter, the flower moon of spring, the hunter's moon of autumn. Each name was a testament to how intimately human life was tied to lunar rhythms. Yet even as people wove tales about our moon, they began noticing that other lights moved across the heavens too. The 5 wanderers we now call planets were known to ancient stargazers, but it wasn't until the invention of the telescope that humanity discovered those planets had moons of their own. That revelation came in the early 17th century and upended our understanding of the cosmos. On a clear January night in 1610, an Italian mathematician named Galileo Galilei pointed his homemade telescope at Jupiter, a shining point in the sky. What he saw astonished him. Near that planet were 4 star-like dots, invisible to the naked eye, that changed position each night. At first, Galileo thought these might be background stars, but as he tracked them, he realized they were orbiting Jupiter. In a letter, he marveled that he had found 4 wandering stars circling a world other than Earth. These were the moons Io, Europa, Ganymede, and Callisto, the first moons ever observed beyond our own. Their existence was a revelation. Here was proof that not everything revolved around Earth. The discovery of Jupiter's moons showed a mini solar system in its own right, with moons dancing around a giant planet, just as Copernicus had dared to suggest that Earth dances around the sun. Galileo's discovery was met with awe and controversy. The idea that moons orbited Jupiter challenged the prevailing belief that Earth was the fixed center of all celestial motion. Yet the evidence was literally before Galileo's eyes. Night after night, he watched those moons shuttle back and forth around Jupiter. It was as if he had invited the heavens to divulge a secret. Other worlds have their own companions. His findings, published in Sidereus Nuncius, electrified Europe. Suddenly, the moon was not unique. It was one of many, and the universe seemed far larger and more complex. The discovery tide did not stop with Galileo. As telescopes improved, astronomers found that Saturn, too, had moons. First Titan, spotted by Christian Huygens in 1655, and then additional moons by Giovanni Domenico Cassini in the following decades. They noticed Saturn's rings as well, mistaking them at first for moons or odd appendages until their true nature became clear. In 1671, Cassini observed Iapetus, a moon of Saturn that intriguingly seemed bright on one side of its orbit and dark on the other, hinting at exotic surfaces that would much later be explained. By the 18th century, the hunt for moons expanded to the new planets discovered. Uranus, found by William Herschel in 1781, came with at least a pair of moons. Neptune, discovered in 1846, revealed its largest moon, Triton, just days later when astronomer William Lassell pointed his telescope at the new blue world. Each of these findings added a piece to a grand timeline of discovery. From a single moon known to ancient humans, we grew aware that moons are abundant. By the 19th century, the count of known moons was climbing. Jupiter's count rose beyond the 4 Galilean moons as fainter ones were caught on photographic plates in the late 1800s, and that count would explode in the late 20th and early 21st centuries. Today we know Jupiter has nearly 80 moons, Saturn over 80, and even Uranus and Neptune have dozens among them. With modern telescopes and probes, scientists keep discovering tiny new moons, often captured asteroids or shards of past collisions that add to the rich menagerie orbiting each planet. Our cosmic neighborhood was teeming with satellites, some as large as planets, others small and irregular. The word moon itself broadened from meaning the moon of Earth to a whole category of objects orbiting planets. Through it all, the myths and wonder persisted. For common people in earlier times, scientific discovery didn't immediately erase the moon's magic. If anything, seeing Jupiter's moons through a telescope might have felt like peering into the divine realms once reserved for gods. The moons of Jupiter were even given mythological names: Io, Europa, Ganymede, Callisto, after lovers and companions of the god Jupiter, a tradition Johannes Kepler had suggested. It was as if, even in science, we acknowledged that these newfound worlds deserved to be woven back into the tapestry of myth. By the dawn of the 20th century, humanity had mapped the motions of many moons, yet they remained points of light in our instruments, their true nature still a mystery. We knew their orbits, and in some cases their sizes. But what were they really like? Were they like our moon, rocky and cratered? Or were they entirely different, perhaps harboring secrets unknown? The ancient questions persisted in new forms. And as the stars of discovery aligned, we prepared in the mid-20th century to actually visit one of these distant orbs and see for ourselves. But before that bold leap, another question loomed. How did these moons come to be in the first place? Origins in cosmic collisions and embraces. To understand the origin of moons, we must travel back to the chaotic infancy of the solar system. Back to a time of swirling disks of gas and dust, of nascent planets coalescing and colliding. Moons are born in violence and in grace, in cataclysms and quiet captures. Their origins are as diverse as the moons themselves, each a story of a smaller world coming to belong to a larger one. One path to becoming a moon is to be born alongside your planet, as siblings in the cosmic nursery. In the young solar system, as giant planets like Jupiter and Saturn formed, they were surrounded by whirling disks of gas and rubble, miniature versions of the disk that formed the sun and planets. Within these circumplanetary disks, material clumped together, layer by layer, eventually growing into the moons we know today. Imagine Jupiter as a newborn king surrounded by a swirling court of dust. Over time, that dust gathered into larger pieces, which drew in more material, building up 4 large moons. Io, Europa, Ganymede, and Callisto, the Galilean moons, likely emerged from Jupiter's disk in this way, like pearls forming in the planet's orbit. In this co-creation, the moons inherited an orderly, flat orbit around their planet's equator, circling in the same direction that Jupiter rotates. They are, in essence, the children of Jupiter's youth, born from the same cradle that fashioned the planet itself. But not all moons share this gentle origin. Some are wanderers that strayed too close to a planet and could not escape its gravity. These moons were not born of their planet, but rather adopted. We call them captured moons. Picture a lone asteroid or perhaps a dwarf planet traveling through space, passing near a much larger world. If conditions are just right, the speed, the angle, maybe the intervention of a third body's gravity, the smaller object can be snared, entering into orbit and becoming a moon. Mars's 2 tiny moons, Phobos and Deimos, are thought to be captured asteroids, cosmic wayfarers grabbed by Mars long ago. They are irregular in shape, dark and battered, very much like the rubble in the asteroid belt from which they likely came. Their capture may have been assisted by a chance encounter or the drag of the early Martian atmosphere. Phobos and Deimos now dutifully circle Mars, but their origin in the sky is written in their odd shapes and carbon, rich composition, so unlike the red planet they orbit. The giant outer planets, Jupiter, Saturn, Uranus, Neptune, have many moons that fit this description, small, lumpy, and often with wild tilted or retrograde orbits, as if caught by surprise. Neptune's largest moon, Triton, stands out as an extraordinary case of capture. Triton orbits Neptune backwards on a tilted path, a clear sign it did not form alongside Neptune. Long ago, Triton may have been a solitary dwarf planet roaming the Kuiper belt until Neptune's gravity ensnared it. The capture of Triton was likely a tumultuous event. Neptune may have had a system of its own small moons that were shattered or ejected in the process. Triton, now bound to Neptune, slowly settled into a circular orbit, but its backward journey remains a scar of its past. It is a migrant from the solar system's fringes, now forever circling an adopted planet, destined in the far future to spiral inward as Neptune's gravity inexorably saps its energy. Then there is perhaps the most dramatic birth of a moon, creation by cosmic impact. Our own moon is the exemplar of this violent genesis. In the young Earth's history, about 4.5 billion years ago, our planet was not alone in its orbit. A Mars-sized protoplanet, often called Theia, was on a collision course with the early Earth. In a titanic impact, Theia struck Earth with unimaginable force, shattering itself and ejecting a vast cloud of molten rock and debris into Earth's orbit. The Earth was left molten and reeling, its day perhaps shortened to a frantic 5 or 6 hours. But from the wreckage, a new entity emerged. The hot debris flung into space gradually coalesced, drawn together by gravity. Within a span of only a few years, perhaps even just a few months, as some simulations suggest, the glowing ring of debris gathered into a sphere. This newborn moon was an incandescent orb of magma hovering above a roiling Earth. Over time, it cooled and solidified, taking on the face we recognize today. This giant impact hypothesis, as violent as it sounds, elegantly explains many of the moon's known traits. The Earth and Moon, for instance, are made of the same basic stuff. Lunar rocks brought back by Apollo astronauts bear the chemical fingerprints of Earth's mantle. It's as if the moon was once part of Earth, which indeed, in this scenario, it was. The collision gouged out material from Earth and mixed it with pieces of the impactor, creating the moon as a blend. The physics of such an impact also explain why our moon is relatively large compared to Earth, and why it orbits in the same plane as Earth's orbit around the Sun, rather than exactly around Earth's equator. It was born of a collision that had nothing to do with Earth's gentle rotation, and everything to do with orbital dynamics and chance. For years, scientists debated alternative theories. Perhaps the moon was captured, or perhaps Earth spun so fast in its youth that a chunk flung off, or that Earth and Moon simply formed side by side. But none of those theories matched the evidence as well as the giant impact. The capture theory struggled to explain the moon's composition, and such a large capture is improbable. The fission idea couldn't account for where the energy to throw off a moon came from. Co-formation didn't explain the differences in iron core size between Earth and Moon. The giant impact, in contrast, gives a dramatic narrative that lines up with the chemical clues. A moon made mostly of earthly material, but lacking heavy iron, and a system still dynamic today. The Earth's moon may be the child of catastrophe, but it forged a new stability. In the aftermath of that impact, Earth gained not only a satellite, but a guardian of sorts, a big moon that would exert a gravitational influence on Earth for eons to come. That story is unique in our solar system. None of the other rocky planets ended up with such a massive moon. It suggests that chance and circumstance, an ill-fated collision at just the right angle and size, can create a moon where otherwise there might have been none. Yet even the giant impact scenario isn't the final word. Scientists continue to refine models of moon formation, debating details. Was Theia completely destroyed? Did the moon form from the debris of both Earth and Theia, or largely from one of them? New theories propose even faster formation or multiple impacts. But the broad strokes remain. Earth's moon was born from fire and chaos, a genesis writ in planetary rubble. Meanwhile, out in the cold reaches of Saturn, another kind of moon formation drama may have played out in miniature. Saturn's iconic rings, made of countless icy particles, might be the cradle for new moons. It's thought that at least one moon of Saturn, a tiny one named Enceladus, may have formed from ring material clumping and merging outside the main rings. And looking at those rings, some scientists speculate they are the remnants of a former moon that wandered too close and was torn apart by Saturn's tidal forces, a fate called Roche limit disruption. If so, Saturn's rings are both a graveyard and a nursery, the destruction of one moon giving birth to perhaps others, as the debris in the rings slowly accretes. Across the solar system, the story repeats with endless variations. Some moons grew calmly from disks, some were snared from elsewhere, some were born in fire and fury. Co-creation, capture, collision. These are the three classic ways to make a moon. Each moon's current orbit and composition carry clues of its birth. A prograde, A lined orbit hints at a native child of the planet. A tilted or backward orbit points to a captured outsider. A large moon, rich in the planet's own materials, whispers of an ancient impact. Understanding these origins is not just cosmic genealogy, it also sets the stage for everything that comes after. A moon's beginning determines its size, its composition, its proximity to its planet, all factors that influence whether it might have an atmosphere, geological activity, or even the ingredients for life. Our journey through the origins of moons, then, is more than an origin story. It's the prologue to every tale of tides, eclipses, volcanic eruptions, and possible life that moons might eventually host. From the dust of creation to the flames of collision, the birth of moons is a drama that has shaped the very architecture of our solar system. And nowhere is the effect of a moon's existence more profound than right here on Earth, where our moon's presence set the stage for the story of life. The moon's imprint on Earth. Our moon, born of Earth's fury, has in turn been a gentle sculptor of Earth's destiny. Once the moon coalesced and cooled, it settled into orbit around our planet, and a gravitational relationship began that continues to this day. This constant companion, comparatively large and close, exerted forces on the young Earth that would slowly weave the conditions for a stable, life-bearing world. The influence of our moon is profound, shaping the tides, steadying the seasons, perhaps even nudging life's evolution from sea to land. Stand on a beach and watch the ocean, and you are seeing the moon's handiwork. The tides, those regular risings and fallings of the sea, are primarily a consequence of the moon's gravitational pull. As the moon orbits Earth, its gravity draws a bulge of water toward it, causing high tide on the side of Earth facing the moon, and simultaneously on the opposite side due to inertia. Our rotating Earth carries coastlines into these bulges and out again, producing 2 high tides and 2 low tides each day. Since antiquity, coastal peoples have timed their lives by this tidal rhythm. Fishermen knew the best harvest of clams or fish often came with the outgoing tide, and navigators planned departures by the high tide's depth. But beyond human use, tides were a mixing spoon in Earth's primordial soup. In the planet's youth, when the moon orbited much closer, tides were enormous. Imagine ancient shorelines with waves tens of meters higher, flooding far inland, and then retreating twice a day, every day. These vigorous tides may have created countless tide pools along rocky coasts, trapping water and concentrated chemicals, then stranding them to dry in the sun before flooding again. Some scientists speculate that these wet, dry cycles, driven by lunar tides, could have been crucial in assembling the complex molecules of life. Perhaps the moon played midwife to life's emergence, providing the gentle pulsation that encouraged simple chemicals to organize into self-replicating patterns. Over billions of years, the moon has been slowly moving away from Earth, and the days on Earth have been growing longer. In Earth's infancy, a day might have been only 6 or 8 hours long, blurred by the rapid spin left over from the moon, forming collision. But the moon's gravity raised tidal bulges, not just in the oceans, but in Earth's solid body as well. As Earth rotated, these bulges lagged slightly behind the line toward the moon, effectively pulling back on Earth's rotation like a brake. The energy of Earth's spin transferred to the moon's orbit, pushing the moon farther away. Through this cosmic friction, our day lengthened from a frenetic spin to the 24-hour cycle we now find so normal. We live, in a sense, on a tempered planet, tempered by the gravitational tug of the moon. If you could speed up time, you would see Earth's rotation slowing and the moon spiraling outward in a graceful, ever-widening helix. And as trivial as a few extra hours in a day might sound, the slowing of Earth's spin and the stabilization provided by the moon had cascading effects on climate and life. One of the most crucial roles the moon plays is as a stabilizer of Earth's axial tilt. The tilt of Earth's axis is what gives us seasons. Leaning toward the sun brings summer, leaning away brings winter. But that tilt is not fixed in space. Gravitational tugs from the Sun and other planets cause Earth to wobble like a spinning top. Without our moon, these wobbles could have been chaotic and extreme. Mars, for example, lacks a large moon, and its tilt has swung wildly over eons, perhaps ranging from near zero to as much as 60 degrees, contributing to violent climate shifts. Earth, by contrast, has the moon's steadying gravitational hand. The moon's mass helps keep Earth's tilt oscillating only mildly over very long timescales, preventing wild swings. This means our seasonal cycle has remained relatively stable for millions of years at a time, providing a consistent backdrop for life to adapt to. If Earth's tilt were to vary dramatically, ice ages might deepen and last longer, or tropics might swing from boiling to freezing, conditions that would challenge the persistence of complex life. The moon's presence has been like the weight on a gyroscope, damping the wobbles and ensuring that the pendulum of climate doesn't swing too violently. Climate stability is more than a comfort. It may have been a key ingredient for life's long, slow evolution. Under a stable seasonal rhythm, ecosystems have time to establish, and species can adapt at an evolutionary pace, not constantly reset by catastrophic climate lurches. Consider that our current mild wobble leads to cycles like the ice ages. Even those relatively mild oscillations challenged early humans, but life as a whole persisted and diversified through them. Had Earth's obliquity swung from 0 to 60 degrees on a whim, the planet might have seen periods where the poles pointed directly at the sun and then later rolled on its side. The moon's steadying gravitational anchor likely spared Earth such extremes. Beyond physics and climate, the moon has subtly guided the rhythms of living creatures. The night's brightness under the moon has steered behaviors for untold species. Sea turtles, for instance, hatch on beaches by the thousands and instinctively crawl toward the brighter sea horizon, using the moonlit ocean to find their way. Salmon and grunion fish coordinate their spawning with the highest tides around the full and new moons, laying eggs in sand that will be washed out on the next spring tide. Corals in the Great Barrier Reef spawn en masse on certain nights linked to the moon's phase, releasing millions of eggs and sperm in miraculous synchronicity under a full moon's light. Even some birds use the moon and stars to navigate during migrations. And ancient human cultures, without electric light, lived by the lunar calendar, planning hunts and festivals by the fullness of the moon. Our very sleep cycles and moods have, anecdotally, been tied to the moon's presence. It's possible that life as we know it has a debt to the moon that we are only beginning to understand. In Earth's deep past, perhaps around 400 million years ago, the moon was closer and tides were stronger. Some research suggests that these strong tides could have influenced the great leap of life from water to land. Fish in tidal pools, trapped by receding water, may have needed to flop to adjacent pools or adapt to breathing air for hours until the water returned. Those that managed such feats survived to pass on traits for air, breathing, and limb, like fins. Over generations, these pressures might have encouraged the evolution of amphibious fish, a stepping stone to true land vertebrates. In this way, the moon's tidal pull might have been an unseen hand, coaxing creatures onto dry land and into a new world of evolution. The moon's influence extends to the invisible choreography of Earth's motion as well. The gravitational dance between Earth and Moon has locked the Moon's rotation to match its orbit. But Earth, too, is moving in response to the Moon. The two actually orbit a common center of mass, a point inside Earth, but offset from its exact center. This wobble means Earth's path around the Sun is slightly perturbed by the Moon's presence. And during solar eclipses, when Moon and Sun align, the Moon's shadow races across Earth, a tangible reminder of how perfectly the Moon can sometimes position itself thanks to its influence on our orientation. All these effects, tides, day length, axial stability, biological rhythms, underscore a profound truth. Without the Moon, Earth would be a very different world. perhaps life would have found a way regardless. Many scientists debate just how critical the moon's presence was for life's eventual emergence and persistence. Some argue that life could adapt to any sky, while others point out that our large moon might have accelerated evolution or even been necessary to get it started. What is certain is that the moon has been intertwined with life's saga at every turn. From the gentle night light that enabled nocturnal creatures to thrive, to the tidal heartbeat that mixed nutrients in the seas, to the steady seasons that allowed complex ecosystems to develop, the moon has been a constant, subtle, guiding force. Tonight, when you see the moon's bright disk or its thin crescent hanging in the sky, remember that its presence is not just aesthetic. That gleaming orb has been working for eons, pulling on our oceans, slowing our spinning globe, and lighting a path for life to follow. It is easy to imagine an ancient Earth without a moon, a dark night sky, weaker tides, a planet wobbling in uncertainty. Perhaps such an Earth would still harbor life. But would it have been the same rich tapestry we know? Our moon has been a blessing of stability amidst cosmic chaos, an ever-present partner that turned what could have been a more erratic planet into a gently pulsating cradle for life. In the grand tale of Earth, the moon is a character impossible to ignore, an influence from the skies that has quietly guided the unfolding of our own story. Now, having appreciated how our singular moon has shaped us, we turn our eyes outward again. For as unique as Earth's moon is, it is but one of a vast menagerie. Out beyond our planet, orbiting the other giants of the solar system, are moons of ice and rock that reveal an astonishing diversity of nature's creations. Our moon's story is intimately tied to Earth. What wonders and surprises might the moons of other worlds hold? It is time to leave home and voyage into the outer solar system, where moons abound and each holds its own secrets. A tour of the solar system's moons, diversity of worlds. Leaving Earth behind, we venture across the solar system to visit the remarkable moons that orbit other planets. Each is a world with its own character, as different from one another as deserts are from glaciers, as fire is from ice. In this journey, imagine flying alongside a spacecraft, sweeping first into the realm of the inner solar system, and then outward past the giants, touching down in thought on one moon after another. Our first destination lies near the roiling clouds of Jupiter. As we approach the giant planet, a speck glowing in golden hues comes into view. Io, the innermost of Jupiter's Galilean moons. At first glance, Io's surface is mottled yellow and orange, like a pizza covered in sulfurous cheeses and sauce. This bizarre coloring hints at the extreme volcanism underneath. Io is the most volcanically active body in the solar system. As our mental spacecraft hovers above Io's alien plains, we see volcanoes erupting in great plumes, spraying molten sulfur hundreds of kilometers high. Lakes of lava glow in red patches across the night side. The ground is coated in sulfur compounds, painting Io in brilliant shades of yellow, white, and green. How did this small moon become a hellfire of activity? The answer lies in the relentless pull of gravity and dance of orbits. Io is caught in a gravitational tug of war between Jupiter and the outer Galilean moons. As it orbits, Io is continuously flexed by Jupiter's immense gravity. Imagine the solid ground rising and falling by tens of meters, squeezed like a stress ball. This tidal heating cooks Io's interior and fuels its prodigious volcanoes. Here on Io, we witness a world in constant upheaval, its surface renewed by fire every few years. It is a land of perpetual change, with mountains taller than Everest, that may only last a few million years before collapsing under Io's geological frenzy. In mythology, Io was a maiden pursued by Zeus, transformed into a cow. In reality, Io is a tortured world, eternally writhing under the grip of its giant overlord. Next, we glide outward to Io's neighbor, Europa. Instantly, the scene changes from fire to ice. Europa is slightly smaller than our moon, and it gleams like a pearl, its surface a smooth, bright expanse of water ice. As sunlight glints off its frozen crust, we see a network of dark streaks crisscrossing the moon, like the cracked shell of an egg. These are Europa's famous lineae, fissures in the ice that have been filled and stained by materials from below. Unlike crater, scarred Callisto, or Mercury, Europa's surface has relatively few craters, indicating it is young and active. But unlike Io, we do not see volcanoes of molten rock. If Europa is active, it is a hidden activity beneath the ice. Scientists have long hypothesized, and now have strong evidence, that beneath Europa's icy shell lies a global ocean of liquid water, kept warm by the same tidal forces that torment Io. This means that as we float above Europa, below us could be an ocean tens of kilometers deep with more liquid water than all of Earth's oceans combined, sealed under a crust of ice perhaps 20 kilometers thick. Occasionally, our spacecraft might catch sight of a geyser, a faint misty plume erupting at the limb of Europa, evidence that water from below sometimes escapes to space through cracks, just as a whale might exhale a breath into the sky. On Europa's surface, we see shattered plates of ice that look as if they've rafted and drifted, and reddish-brown stains where salts or organics may have upwelled. It's a relatively flat world, no towering mountains, but rather a jigsaw puzzle of ice. If we could land and drill down, we'd eventually break through into an alien sea. In our mind's eye, we plunge into the dark waters of Europa, shining a light into the depths. What might we find? Perhaps the seafloor of Europa has hydrothermal vents, like those on Earth's ocean bottom, where mineral-laden hot water gushes out of rock, providing energy and nutrients. On Earth, such vents teem with life: tube worms, clams, strange microbes, entire ecosystems cut off from sunlight. Could Europa's oceans similarly harbor life, nourished by chemical energy and warmth from below? It's a question so enticing that humans are planning missions to one day pierce Europa's secrets. For now, as we leave Europa, we feel the profound hush of this moon, a still, glistening surface above a hidden, restless sea. If Io is the solar system's volcano, laden heart, Europa is its enigmatic, icy soul, holding its secrets deep under frozen plains. Continuing outward, we meet Ganymede, the giant among moons. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury. As we approach, Ganymede looks somewhat like a scaled-up version of our moon or Mercury, with light and dark patches. But Ganymede has a surprise. It possesses a magnetic field of its own, something no other moon has. Our spacecraft instruments detect the auroras shimmering in Ganymede's thin atmosphere, proof of its magnetic bubble within Jupiter's powerful magnetosphere. Ganymede's surface is a mix of very old, dark, cratered regions and somewhat younger, lighter regions laced with grooves and ridges. It's as if Ganymede tried to undergo tectonic activity in its past, the crust stretching and breaking into patterns, then largely froze in place. Like Europa, Ganymede is believed to have an ocean beneath its surface, but likely sandwiched between layers of ice, perhaps a deep, buried sea that is less accessible. Still, the presence of water, a differentiated interior with a metal core, and that enormous size make Ganymede a world of interest. If we could stand on Ganymede, we'd see Jupiter looming huge in the sky, and perhaps thin wisps of oxygen around us. We might walk on water, ice that is, that conceals a distant ocean below our feet. Next comes Callisto, the outermost large moon of Jupiter, a stark contrast to the others. Callisto, shrouded in darkness at the fringes of Jupiter's domain, appears as an ancient cratered relic. Its entire face is pockmarked like a cosmic shotgun target, saturated with impact scars from eons past. It has no discernible mountains or volcanoes or ridges, just endless craters upon craters, with faint rings around the largest impacts. like ripples frozen in ice. If the inner moons of Jupiter are active or were active, Callisto seems to have never been. It is, in a way, a long dead world, a remnant of the early solar system preserved in cold storage. Yet even quiet Callisto might hide a small secret. Data from spacecraft hint it too could have a slumbering ocean deep inside, beneath hundreds of kilometers of ice and rock. If that ocean exists, it has likely been static for billions of years, undisturbed by significant heating or tidal flexing. Callisto stands as a testament that not every moon becomes a geologic wonderland. Some simply exist, surviving from antiquity with the stories of the solar system's violent birth written in their craters. Leaving Jupiter, we sail on to Saturn, where a multitude of moons awaits in a realm of icy enchantment. The first to greet us is Titan, Saturn's largest moon and one of the most compelling places in the solar system. As we approach Titan, we do not see a cratered moon at all. Instead, we see a hazy orange sphere, its surface completely hidden by a thick atmosphere. Titan is the only moon with a dense atmosphere. In fact, at Titan's surface, the atmospheric pressure is about 1.5 times that of Earth's. Standing on Titan would feel a gentle weight of air around you. This atmosphere is rich in nitrogen, like Earth's, but suffused with methane. High in Titan's skies, methane and other hydrocarbons form thick smog that filters the sunlight to a dim, amber glow. If we descend through Titan's clouds, we would witness a landscape both alien and uncannily familiar. There are rivers and lakes here, but filled with liquid methane and ethane instead of water, for Titan's surface temperature is a frigid 179 degrees, far too cold for liquid water. In Titan's dim noon light, we might see ethane rain falling from the clouds onto broad, mirror-like lakes that stretch to the horizon. There are rolling dunes made of hydrocarbon sand, likely formed from organic molecules that have settled out of the sky. There are even seasons on Titan. Over its 30-year orbit around the Sun, its polar lakes shrink and grow, and clouds cluster in different regions. Titan is a world that eerily parallels Earth in some ways. Wind, rain, rivers, lakes, maybe even cryovolcanoes that erupt not molten rock, but water mixed with ammonia from its icy interior. Beneath Titan's frozen crust, scientists suspect another hidden ocean of liquid water and ammonia might reside, kept warm by the moon's internal heat. Titan thus could have two kinds of habitable zones, one in its dark subsurface ocean and another in the liquid hydrocarbons on its surface, albeit any life that might exist in the latter would have to be very different from life as we know it. As we roam Titan's surface in our imagination, methane rain falls on our helmet visor and pools at our feet. We see the glint of Saturn's rings in the sky through a gap in the clouds. Titan feels like a primordial Earth, but one locked in deep freeze where chemistry, not biology, paints the scene. Not far from Titan, another small moon beckons with a dazzling display. Enceladus. Compared to Titan's enormous diameter of 5,150 kilometers, Enceladus is tiny, only about 500 kilometers across. Yet what Enceladus lacks in size, it makes up for in wonder. This bright, ice-covered moon orbits within Saturn's E-ring, and as we draw near, we see why that ring exists. Enceladus is actively spraying its material into space. Along Enceladus's south pole, great fissures in the ice, fondly called tiger stripes, crack the surface. From these cracks, geysers of water vapor and ice crystals continuously erupt, like a curtain of fine, misty jets. Our spacecraft flies through one of these plumes, and instruments taste the vapor. They find water, simple organic molecules, and even microscopic grains of silica, hinting at hydrothermal vents down in a warm ocean beneath the ice. Enceladus, like Europa, hides an ocean under its shell, and through those tiger stripes it vents the ocean to space, giving us free samples of what lies beneath. The sight is breathtaking. Against the blackness of space, dozens of geysers catch the sunlight, forming a shimmering halo over the moon's south pole. The surface around the area is young and smooth, repaved by fresh icefall from these plumes. It was the Cassini spacecraft that discovered this surprise in 2005, changing forever how we see this moon. We now picture Enceladus as a small, cold world that nonetheless has become a cosmic snow globe of activity. Its internal heat likely comes from tidal flexing, which keeps its core warm enough to maintain a liquid ocean. The water from that ocean, maybe 30 kilometers below, forces its way up through cracks and sprays out, instantly freezing and falling back, or floating away to feed Saturn's rings. If we land near a tiger stripe, we'd be on terrain of pure water ice, possibly feeling the ground tremble from subsurface activity. It would be unimaginably cold on the surface, but just below might lie liquid water and perhaps geothermal vents rich in minerals, again raising that tantalizing possibility. Could life exist there, swimming in a hidden sea and periodically being shot out through a space geyser? Now we venture further out, past Uranus with its retinue of frozen, dark moons. We arrive at Neptune, the outermost giant, where a captured moon reigns. Triton. Triton is Neptune's largest moon and unlike any other in the outer solar system. When Voyager 2 flew by in 1989, it revealed Triton as a pinkish, icy sphere with a polar cap of nitrogen ice and a strange cantaloupe-textured terrain. Triton was a revelation. Despite being far from the sun and in the deep freeze, it was not entirely inert. Voyager's cameras caught sight of dark, wind-blown streaks and, incredibly, active geysers near Triton's south pole. But these were not water geysers like Enceladus's. Triton was spewing nitrogen gas. Invisible sunlight, though weak, was enough to heat darker patches on Triton's surface, causing pockets of nitrogen ice to turn to gas and erupt through the surface, carrying dark soot like particles that then fell back, streaking the landscape. We witness one of these geysers ourselves, a faint geyser, backlit by the dim sun, reaching some kilometers high before the material drifts downwind in Triton's thin atmosphere. Triton's surface is young in many areas, with few craters, indicating it has been resurfaced, perhaps by icy volcanism or other processes. We glide over plains that may have been smoothed by slush or eruptions of water, ammonia mixtures long ago. There are odd, lumpy landscapes that look like melting ice cream, possible signs of past cryovolcanoes. Triton, being a captured object, has an eccentric past. Its capture by Neptune would have generated immense tidal heating at first, potentially melting its interior. Over time, Triton settled into a retrograde, circular orbit and cooled, but the geological memory of that event is written in its relatively complex geology. Triton orbits Neptune opposite to the direction Neptune rotates, which is unique for a moon of that size, another clue of its exotic origin. It is also slowly spiraling inward. One distant day, far beyond our lifetimes, Triton may come close enough to be torn apart by Neptune, perhaps forming new rings. But for now, it's a frozen moon with a thin air of nitrogen, a wintry outpost showing that even in the far reaches of the solar system, moons can be dynamic. As our journey through the solar system's moons comes to an end, we take a moment to appreciate the staggering variety we've encountered. We flew from Io's lava fountains to Europa's secret ocean, from Ganymede's giant bulk to Titan's orange skies and methane lakes, from Enceladus's crystal plumes to Triton's geysers and icy plains. We saw moons that could fit in a small sea on Earth, and moons bigger than planets. We saw fire, ice, atmospheres, magnetic fields, and underground seas, all in worlds that orbit other worlds. Each of these moons is a chapter in the solar system's story, a unique expression of how diverse planetary bodies can be. It's humbling to remember that for most of history, these places were just points of light, or in Titan's case, not even visible under its shroud. Only recently have we glimpsed their surfaces and felt their environments, through our robotic emissaries. They have transformed our understanding of what a moon can be. No longer can we think of moons as mere dead rocks orbiting planets. Many are complex, geologically alive, and in several cases, potentially harboring the conditions for life. Our tour has shown us boiling sulfur and freezing methane, stark craters, and ethereal atmospheres. And yet, among all these differences, each moon shares a common role, circling a parent planet, locked in a gravitational embrace. They light up their planet's night skies, just as our moon lights ours, each one a smaller part of a greater whole. With this rich tapestry of moons in mind, we are drawn to wonder, where else in those distant, cold, or hot moons might life have found a foothold, as it did on Earth's congenial world under the influence of our moon? The next leg of our journey delves deeper into that question, focusing on those moons that tantalize us with conditions that could be ripe for life. Oceans and the search for life on moons. Among the myriad moons we've visited in our imagination, some stand out as more than just geological wonders. They stir the question of life. Could any of these alien moons harbor living organisms, or at least the ingredients for life's chemistry? The possibility is no longer science fiction. It is a serious focus of modern planetary science. Particularly, the moons that conceal liquid water beneath their surfaces have captured our hopes. On Earth, where there is water, there is life, virtually everywhere. So what of those moon oceans in eternal night? Could life be swimming in Europa's abyss, or lurking in Enceladus's geysers, or even riding the methane raindrops on Titan? The case for Europa as a habitat begins with its deep saltwater ocean, which could be tens of kilometers thick and global, containing perhaps twice the volume of all Earth's oceans. Liquid water alone is enticing, but life also needs energy and chemistry. Europa seems to offer those as well. Jupiter's constant tidal kneading not only keeps Europa's ocean liquid, it likely drives geological activity at the sea floor. If Europa's rocky mantle interacts with its ocean, perhaps through hydrothermal vents, there could be warmth and nutrients feeding into the water. On Earth, life thrives around hydrothermal vents in the lightless depths, drawing energy from chemical reactions. Europa could host analogous ecosystems, microbes or more complex life feeding on the chemical energy from inside Europa. The European Ocean is sealed off by ice, but that ice might also do something important. It could cycle nutrients. We saw Europa's surface is crisscrossed by cracks and regions where ice seems to have moved around. Some scientists think that surface oxidants could be transported downward through the cracks or subducting ice plates, providing chemical food for life below. In essence, Europa might have the three key ingredients: liquid water, chemical building blocks, and an energy source. No one knows if anything actually lives there. It remains a profound mystery. But if one day we were to drill through Europa's ice and drop a submersible, we might find a whole ecosystem of alien microbes or pale blind fish analogues gliding through the dark. Or we might find nothing at all but a sterile sea. Yet as long as that ocean is there, Europa will beckon as one of the best places beyond Earth to search for life. Then there's Enceladus, the little moon that surprised us with a direct invitation to sample its ocean. Enceladus's plumes jetting into space provide a literal taste of its subsurface sea. When the Cassini spacecraft flew through those geysers, its instruments detected organic molecules, including some fairly complex ones, and tiny grains of rocky particles that could only be formed by hot water interacting with rock. This was a smoking gun for hydrothermal vents on Enceladus's seafloor. Moreover, in 2023, scientists announced that those icy grains contained phosphorus, an element crucial for life, which had been a missing puzzle piece in evaluating Enceladus's habitability. In one swoop, Enceladus offers water, organics, and key minerals, an entire chemistry set for life. The energy clearly exists too. Something drives those plumes, and presumably it's heat from below. Enceladus is small, which suggests its ocean might be in contact with a rocky core that's being flexed and heated. If one could dive into Enceladus's ocean, would it be a dead, dark sea? Or might one find microbial mats around warm vents? Or maybe some exotic life forms that evolved entirely independently of Earth? We cannot help but wonder. Unlike Europa, where a thick crust makes direct exploration challenging, Enceladus conveniently sprays its ocean into space, making it easier for a spacecraft to analyze for signs of biology, perhaps complex organic compounds, or even traces of cells or their remnants in the ejected ice. Titan presents a very different potential for life. On Titan's frigid surface, the lakes and rivers of methane and ethane form a chemistry that is likely too cold and too alien for Earth, like life. Water there is locked up as rock, hard ice. If life exists on Titan's surface, it would have to be something that drinks liquid methane instead of water, a truly novel biochemistry that we can only speculate about. Some astrobiologists have mused about methanogenic life, creatures that use liquid hydrocarbons as a solvent and perhaps breathe hydrogen and exhale methane, but this is highly hypothetical. Titan's surface environment is so cold that reactions happen slowly. It might be tough for life to get started. However, Titan is rich in organic molecules. The atmosphere and surface are a laboratory of prebiotic chemistry, where sunlight breaks apart methane and nitrogen, forming carbon, rich compounds that rain down. Titan's smog is literally a shower of organic matter. Some liken Titan to a deep freeze version of the early Earth's chemical soup, minus the liquid water. While surface life is speculative in the extreme, Titan also, intriguingly, likely has a subsurface water ocean beneath its ice crust. So Titan might have two environments of interest: a cold surface with exotic chemistry, and a hidden water ocean where more familiar life could conceivably exist. If there is life in Titan's ocean, it would be completely cut off from the surface, evolving in the dark with perhaps only the faint trickle of chemical nutrients from rock and ammonia antifreeze to keep it liquid. It's a far cry from the rich brew of Enceladus or Europa, but Titan surprises us at every turn, so who can say? Even Ganymede and Callisto, those Jovian moons we thought rather inert, may harbor deep oceans beneath thick ice layers. Ganymede's ocean is likely sandwiched between ice, which might limit its habitability. Callisto's ocean, if it exists, is also entombed. These places seem less likely abodes for life, but until we explore them, the possibility, however remote, remains. Triton at Neptune, too, could have had a subsurface ocean when it was younger, and maybe pockets remain today, though it's hard to imagine life surviving the drastic upheavals of Triton's capture and cooling. What about moons without oceans? Could life exist in some other form? Perhaps not life as we know it. Moons like Io are too hostile, bathed in radiation and molten rock. Luna is bone, dry and airless at the surface, though we've found traces of water ice in its shadows. It seems lifeless. Most small moons are like asteroids, inert, with no air or water. So it is the water, rich moons that raise our hopes. Our exploration so far has been like detectives gathering clues. Water plumes here, organic molecules there, heat signatures hinting at liquid below. No definitive evidence of life has been found beyond Earth, but these moons offer some of the most promising hunting grounds. In a way, the search for life on moons has reshaped our idea of the habitable zone. We once thought you had to be at just the right distance from the sun for a planet to have liquid water and life. But Europa and Enceladus show that a moon can have liquid water far outside the traditional habitable zone, thanks to tidal heating. So perhaps in other solar systems, moons of giant planets might outnumber planets as places to find life. The thought is exhilarating. Life, bearing moons orbiting massive Jupiter, like planets in distant star systems, or under the ice of Saturn's modest satellites. If we find even simple organisms in one of these moons' oceans, It would suggest that life might spring up wherever conditions allow, even in the dark, under kilometers of ice, given water and energy. If, on the other hand, we search thoroughly and find nothing living in these seemingly habitable oceans, that would also teach us something profound, that perhaps life is more rare or needs more specific circumstances than we think. For now, these questions propel us to keep exploring. Planned missions like Europa Clipper will sniff out Europa's environment for chemical signs of life's work. Future concepts imagine sending a probe through Enceladus's plume specifically equipped to detect biomolecules or even cells. There is even a dream of one day sending a lander to drill into Europa's ice, or a submarine to swim in its ocean. As we contemplate these moons with potential for life, we feel a subtle shift in perspective. No longer are we the center of the living universe. Life could be scattered on these little ocean worlds in our own celestial backyard. Imagine looking up at Jupiter in the sky and knowing that on one of those pinprick moons orbiting it, something stirs in an alien sea. Such a realization would forever change our relationship to the cosmos. In the grand scale of the solar system, these moons are tiny, but in their tiny niches they may hold some of the biggest answers. Are we alone, or is life a common melody threaded through many worlds? To find out, we must continue to explore these moon worlds with open minds and meticulous science. And as we do, we deepen our appreciation of how special and varied moons can be. Not just passive satellites, but active worlds that could nurture life in the most unexpected of places. Having pondered life and hidden oceans, we turn now to look at moons in another light, as dynamic worlds with geological stories of their own. Alive or not, these moons are far from static. Some are alive geologically, with volcanoes of fire or ice, shifting crusts, and evolving surfaces. Let us now examine how moons, much like planets, can be volcanic, tectonic, and surprising in their ongoing activity. Geological marvels, volcanoes, geysers, and tectonics on moons. In exploring moons, we have discovered that many are not inert balls of rock, but geologically dynamic worlds. Just like planets, moons can have volcanoes that erupt molten rock or icy slush, quakes that shake their crusts, and tectonic forces that reshape their surfaces. These processes remind us that size and status don't limit geological vitality. What matters is energy. If a moon has internal heat, from tidal flexing, radioactive decay, or leftover heat of formation, it can become a stage for remarkable geological activity. Let's examine some of the ways moons act as living worlds of stone and ice. First, consider volcanism. We traditionally think of volcanoes as mountain cones on Earth, spewing lava, or the great basalt floods that created our moon's dark seas billions of years ago. But on Io, as we saw, volcanism is an ongoing symphony of fire. Io's volcanoes, like the towering plume of Loki Patera or the curtains of lava at Prometheus, are driven by tidal heating. This is a fundamentally different heat engine from Earth's radioactive core-driven volcanism, and it makes Io's entire surface a volcanic canvas. Lava flows hundreds of kilometers long repaint Io's face, and enormous calderas dot its surface. Io's volcanism is so intense that it constantly replenishes a thin atmosphere of sulfur dioxide, and even feeds a giant torus of plasma around Jupiter. We have effectively seen a tiny moon outdoing even Earth in volcanic output, all because it is squeezed by gravity like putty. Our own moon once had its fire, a fact written in the vast mare which are solidified lava from ancient eruptions. Though the moon is quiet now, for the first billion years of its life it saw eruptions flood craters and lowlands with basalt. Even small moons can erupt. Take Jupiter's moon Io as the prime example, but also Saturn's tiny moon Enceladus, where cryovolcanism, volcanoes of water, not fire, operates. Cryovolcanism is essentially the cold region equivalent of volcanism. Instead of molten rock, what erupts is liquid water, or water mixed with ammonia or methane that can flow at very low temperatures. Enceladus's geysers are cryovolcanic in nature. There might also be cryovolcanoes on Triton, and possibly on Titan. In fact, Titan's surface shows some features that scientists interpret as potential ice volcanoes. For example, a feature named Doom Mons appears to be a broad rise with a pit, reminiscent of a volcanic caldera, and nearby flows of what could be once melted ice. If Titan has cryovolcanoes, they could be venting water and ammonia from its interior, perhaps occasionally refreshing the surface or atmosphere with new material. Tectonics, the forces that crack and shift a crust, are also present on moons. We have only confirmed active plate tectonics on Earth, but evidence of tectonic-like processes can be found on moons. Europa's cracked ice plains strongly hint at an ice crust that has pulled apart and maybe even subducted in places, as one plate of ice slides under another, similar to Earth's geological plates. Ganymede's network of grooves and ridges suggests that at some point in its past, its icy lithosphere was stretched and pulled, creating faults and troughs, akin to rift zones on a planet. Even small Enceladus shows tectonic fractures. Its surface has regions of tight, rippling faults and folds, especially around the South Pole, indicating the crust has been stressed, distorted by cycles of freezing and thawing, or the stresses from its orbit. Miranda, a small moon of Uranus only about 470 kilometers across, is a bizarre example. It sports giant canyons and patchwork terrain that might have formed from tectonic upwellings or even a reassembly after a shattering impact. It's as if Miranda was broken apart and gravity put it back together in a jumbled way, leaving huge cliffs and chevron-like surface regions. Resurfacing is another sign of geological life. A surface that doesn't stay cratered but is renewed. We gauge a surface's age by how cratered it is. The more craters, the older. When we see a moon like Callisto, saturated with craters, we suspect it's been geologically quiet for billions of years. In contrast, Europa's relatively smooth, crater-poor surface means something erased the craters, likely the movement of ice or flooding of fresh material. Io's lack of many impact craters is explained by its volcanoes constantly burying them. Enceladus has certain regions with almost no craters. Clearly, it has been resurfaced by ongoing geyser activity, laying down fresh snow, like ice. Titan's craters are few and far between, likely because active processes like wind erosion, liquid methane rain carving river channels, and perhaps cryovolcanism all conspire to modify the surface. A fascinating example of resurfacing is Iapetus, Saturn's odd two-toned moon. While not exactly resurfaced by internal activity, it has sweeping dark material coating one hemisphere, likely fallout from dust or perhaps cryovolcanic material from outside. The contrast on Iapetus shows how surfaces can change due to even external processes. Then there are moonquakes and other internal rumblings. Apollo astronauts left seismometers on the moon, and they detected that the moon isn't dead silent. There are moonquakes, some from tidal stresses, some from thermal changes, and some from the occasional meteorite impact. The moon's quakes are mild compared to Earth's, but they tell us our moon still settles and adjusts. In recent years, we've even found evidence that the moon shrinks very slowly over time as it cools, forming fresh scarps and cliffs where the crust has cracked and pushed up. Some of these faults look so sharp and young that they may have caused quakes in the moon's recent past. If our large moon can still creak and quake, imagine the much more active churning inside moons like Europa or Enceladus. Some moons have magnetic personalities. Ganymede's intrinsic magnetic field points to a liquid metallic core churning inside, which is a form of internal activity. Even if that doesn't manifest in surface geology, it's an internal dynamic process, and we have induced magnetism detected at Europa and Callisto, hinting at conductive oceans moving within. We also see evidence of expansion or contraction on some moons. For instance, Mercury has shrinkage cliffs. Similarly, as mentioned, our moon has them from contraction. Enceladus's ridges and troughs might indicate cycles of freezing and melting. Triton's weird cantaloupe terrain could be from slow, convective overturn in the ice, a sort of relaxation of the surface. Let's not forget the icy ring moons and how they interact. Some tiny moons like Pan and Atlas around Saturn are sculptors of the rings, their gravity opening gaps and shaping edges. This is a gravitational interaction, but results in geological, like patterns in the ring debris. And some moons like Saturn's Janus and Epimetheus even gently collide and exchange orbits occasionally, though they themselves are too small for internal geology. Their dance is a dynamic process on a celestial scale. What we learn from all these observations is that moons can be as geologically diverse as planets. Being a moon only means it orbits a planet. It says nothing about whether it has volcanoes or not. The presence of internal heat is key. Tidal heating has emerged as a major driver. It powers Io's infernos and Enceladus's fountains, and likely Europa's underwater volcanism. Radioactive decay and leftover heat can drive early activity. Sometimes a huge impact can melt a moon's insides briefly. As we visit these moons as geological worlds, one cannot help but anthropomorphize a little. Io is the restless firebrand, Europa, the secretive ocean, Holder cracking its knuckles now and then, Enceladus, the tiny overachiever, spraying its cosmic fountain, Titan, the atmospheric enigma, slowly raining and eroding, and Triton, the captured rebel, still venting occasional sighs of nitrogen. Even sedate old Callisto, or far out Oberon, and Titania around Uranus each have stories, perhaps long dormant, but written in chasms and craters, waiting for a future mission to decipher. The more we see, the more we appreciate how active and varied moons can be. Gone is the notion that moons are boring backwaters. Instead, we find on these smaller orbs an incredible laboratory of geology. From the hellish volcanism of Io, hotter in spots than Earth's volcanoes, to the gentle ice volcano cryovolcanism of the outer moons, to evidence of tectonics that on Earth would signal plate movements. Moons have witnessed and enacted many of the same processes that shape planets, and some unique ones too. By studying these processes on moons, we also learn more about Earth. Io's tidal heating is an extreme case that illuminates how gravitational energy can geologically transform a body. Europa and Enceladus show what happens when internal oceans interact with crusts, something that might have analogies in Earth's past. Even the moon's slow cooling and shrinking gives insight into how terrestrial planets lose heat. With our geological tour of moons concluded, we have seen worlds alive in one way or another. Now, we turn our attention to some of the anomalies and oddities that defy the typical patterns. The misfits of the moon world, those that are irregular, transient, or just plain peculiar. These include moons that are more like asteroids, moons that come and go, or systems where moons share orbits in a celestial dance. The solar system has plenty of the strange along with the sublime, and in our next chapter, we shine a light on those lunar oddballs and mysteries. Oddballs and mysteries, irregular, ephemeral, and bizarre moons. Not all moons fit the mold of spherical worlds with stable, eternal orbits. The solar system is also populated with moons that are decidedly odd. Some are misshapen chunks, barely held together, looking more like asteroids than moons. Others follow peculiar paths or engage in orbital dances that seem to defy common patterns. A few are only temporary guests of their planets. These oddballs and enigmas highlight the playful creativity of gravity and the remnants of violent histories. First, consider shape. To be round, a moon needs enough gravity to pull itself into a sphere. Many moons, especially smaller ones, lack the mass for that, and instead have irregular, potato-like shapes. Mars's moons. Phobos and Deimos are classic examples. Phobos looks like a battered rock, pockmarked with craters, notably one giant crater that gives it a Death Star-like appearance. Deimos is smoother, having accumulated dust in its craters, but it's lumpy too. These moons are almost certainly captured asteroids, as their shape and composition suggest. They remind us that the line between moon and asteroid can blur. Around the giant planets, dozens of tiny moons likewise are irregular. Jupiter and Saturn each have swarms of little moons out beyond their big moons, often on eccentric or tilted, or even backward orbits. These are captured remnants from the early solar system or fragments of shattered moons. They typically have irregular shapes. Saturn's moon Hyperion is a standout. It's about 270 kilometers across and looks like a giant sponge. Hyperion's surface is bizarrely carved into deep pits, and its density is so low that scientists suspect it's a porous rubble pile that never compacted fully. To top its strangeness, Hyperion doesn't rotate steadily. It tumbles chaotically, its axis wobbling unpredictably due to gravitational perturbations from nearby Titan. If you tried to predict when the sun would rise on Hyperion for a given location, you'd have a hard time. Its spin is that irregular. Another irregularly shaped curiosity is Pan, a tiny moon of Saturn only 35 kilometers across. Pan orbits within Saturn's rings, in the Encke Gap, and has accumulated a skirt of ring particles around its equator, making it look like a flying saucer or a walnut. It has a bulging ridge, essentially a ring of its own, stuck to its equator. Atlas, another little ring moon, has a similar UFO-like look. These ridges likely formed as the moon scooped up dust and ice from Saturn's rings while orbiting within or near them. These mini-moons underscore how moons can shape and be shaped by their environment in surprising ways. Now, binary systems. While no planet besides Pluto truly has a binary moon system where two moons orbit each other around a planet, Pluto and Charon deserve mention. Charon, roughly half Pluto's size, isn't just a moon. Together, Pluto and Charon act like a double dwarf planet system. They orbit a point in space between them, gracefully pirouetting around each other every 6.4 days, forever showing the same face to each other. This mutual tidal locking and the balance of sizes make Pluto-Charon a unique case in our solar system. It stretches the definition of moon, as one could argue Charon is not just orbiting Pluto, they orbit each other. If Earth's moon were a bit larger, Earth and the moon might similarly orbit a point in between. The Pluto-Charon example invites us to consider that in other solar systems, there might be exoplanets with moons so large that the distinction between planet and moon blurs, and they form true binary pairs. Within our solar system's moons, we also see co-orbital dances. Saturn's moons, Janus and Epimetheus, for example, share nearly the same orbit. They are only about 50 kilometers different in their orbital radius, and they race around Saturn in close pursuit. Every 4 years or so, the inner one catches up to the outer one, and they perform a gravitational do-si-do. They exchange energy and effectively swap orbits. The one that was inner moves to the slightly outer orbit, and the outer moves to the inner path. Then the cycle continues. It's a graceful swap that conserves momentum and prevents collision. For a long time, astronomers were confused by observations of what seemed like one moon in that orbit that occasionally jumped position, until they realized it was two. Another strange orbital choreography involves what we call Trojan moons. Two of Saturn's moons, Tethys and Dione, each have smaller moons that reside at the stable Lagrange points, leading or following the bigger moon by 60 degrees in the same orbit. Essentially, the little moons are locked in a gravitational sweet spot, shepherding the orbit of their larger partner. They're like captured attendants, forever preceding or trailing the larger moon. No other example of Trojan moons is known beyond Saturn, but the concept is intriguing. Moons of moons in stable configurations. Temporary moons are a particularly interesting category. Earth, besides our big moon, occasionally has other small mini-moons. These are tiny asteroids captured for a short time. For instance, in 2006, a small asteroid about a few meters in size was captured by Earth's gravity and orbited Earth for several months before drifting away. More recently, another mini-asteroid called 2020 CD3 was discovered orbiting Earth from 2018 until 2020. These temporary moons come and go, usually staying for a few orbits before the dynamics allow them to escape. They remind us that the definition of a moon can be fleeting. A moon can be there 1 year and gone the next. At any given time, Earth might have one or more tiny natural satellites temporarily, and we wouldn't know unless we look carefully with telescopes. Jupiter and other planets likely capture small asteroids on occasion too. Their hills of gravity are larger, but also their real estate is far from Earth, so we notice fewer of those captures. Retrograde moons and inclined oddballs add to the menagerie of strange. Many of the tiny outer moons of Jupiter, Saturn and Neptune orbit backward relative to the planet's rotation. Triton, again, is the largest retrograde moon, captured and forced to dance to Neptune's tune in reverse. These retrograde moons often have stretched, inclined orbits too, suggesting they were snared objects. There are also moons with remarkably eccentric orbits. One of Jupiter's distant moons, S2003J2, loops far out in an oval path, taking years to complete one orbit. Some small Saturnian moons oscillate in strange resonances, like Neptune's inner moons, Naiad and Thalassa. Naiad is in a slightly inclined oval path that bobs up and down in such a way that it avoids ever colliding with Thalassa, in what's been described as a dance of avoidance. Naiad laps Thalassa every few orbits, passing above or below it in a choreographed pattern dictated by resonance. Physical anomalies also intrigue us. Iapetus, Saturn's two-toned moon, aside from its dark light yin-yang coloration, boasts an equatorial ridge of mountains that wraps most of the way around like the seam of a walnut. How did such a ridge form? One theory is that Iapetus might have had a decaying ring of its own that collapsed onto its equator, building a chain of mountains. Or it could be the remnant of Iapetus's youthful spin, when it rotated so fast that the equator bulged and then froze in place as the moon cooled. It remains an odd and picturesque feature, unmatched elsewhere. And what about moons with rings? It sounds fanciful, but Saturn's second largest moon, Rhea, gave a hint of a possible ring system in some spacecraft data. If confirmed, that would be a moon with its own ring. As of now, it's an open question, and subsequent observations haven't clearly found rings around Rhea, so that mystery endures. These irregular, ephemeral, and surprising moons teach us that being a moon is not one size fits all. They are the exceptions that prove the rule, and sometimes they break the rules in delightful ways. They speak to the dynamic and often violent processes that populate planets with moons. Captures of passing objects, collisions that shatter a moon into pieces that become new moons or rings, gravitational tricks that allow multiple bodies to share orbits. They also show us how creative nature can be with orbits. As long as the laws of gravity are obeyed, seemingly odd arrangements can persist for millions of years. If you had an artist's eye, you might see Janus and Epimetheus as two dancers swapping positions on a giant stage, or the Trojan moon Telesto as forever surfing the gravitational wave ahead of Tethys. You might see Hyperion tumbling through space like a tossed sponge from the gods, never the same rotation twice, or Phobos, slowly spiraling inward toward Mars, destined to either crash into the Martian surface or be torn into a ring in some millions of years. A moon in death throes, gradually succumbing to tidal forces. Yes, even the lifespans of moons can be finite. As mentioned, Triton will likely spiral into Neptune someday far off. Phobos is drawing closer to Mars by a few centimeters each year. Within 50 million years or so, it may break apart under Mars's tidal pull, and possibly create a short-lived ring around Mars before raining down. Jupiter's intense gravity may eventually destabilize some of its captured shards as well. The temporary moonlets come and go on human timescales, hinting that the tapestry of moons is still being woven even now. Through these strange moons, we see the solar system not as a static set of clockwork orbs, but as an evolving, changing family with members that sometimes wander in, sometimes wander out, sometimes behave bizarrely. It's a cosmos of surprises. And as we prepare to send more explorers out there, who knows what other odd moons we might find? Perhaps a moon with active geysers of neon, colored chemicals, or a moon that is two halves barely held together, or moons in exotic resonant patterns yet unseen. We now have journeyed through nearly every aspect of moons, their mythic allure, their formation, their effects, their astonishing diversity and geology, and their curiosities. Our attention turns next to how we humans have stepped into this story with our machines and our own feet, through missions that have explored these moons, and how those missions have enriched our understanding and prepared us for even grander adventures to come. Reaching the moons, from Apollo to tomorrow's missions. Humanity's fascination with moons has not remained in the realm of observation and theory. We have boldly taken voyages to these distant worlds, sending spacecraft to uncover their secrets. Each mission, whether crewed or robotic, has been a chapter in our unfolding understanding of moons, transforming points of light into real places with landscapes and histories. Let's journey through some of the landmark missions that have explored moons and look ahead to the missions on the horizon. The first tentative steps were robotic. In the late 1950s and 1960s, during the dawn of the space age, both superpowers, the United States and the Soviet Union, set their sights on Earth's moon. The Soviet lunar program achieved a series of historic firsts: the first human-made object to hit the moon, the first photos of the moon's far side, and later the first soft landing and the first robotic rover. These early missions proved the moon was reachable and prepared the way for something even bolder: landing humans there. In July 1969, the world watched in collective awe as Apollo 11 carried Neil Armstrong and Buzz Aldrin to the Sea of Tranquility. When Armstrong stepped off the lunar module's ladder, uttering, "That's one small step for a man, one giant leap for mankind," a dream as old as humanity was realized. The astronauts found a world of grey dust and rocks under a black sky, Earth hanging blue and bright above the horizon. Aldrin described the lunar landscape as magnificent desolation. Over the course of 6 Apollo missions, 12 humans walked on the moon, exploring different regions, driving a lunar rover across the soil, setting up experiments, and collecting rocks. These samples, returned to Earth, revolutionized lunar science. They told us the moon's composition, its volcanic past, and supported the giant impact theory by revealing the moon's similarity to Earth's mantle. Apollo 8, months before the landing, had already given us the iconic Earthrise photo, Earth rising over the moon's limb, an image that redefined how we see ourselves, a delicate blue marble in the vastness as witnessed from the moon. Apollo ended in 1972, and no human has been beyond low Earth orbit since, marking a pause in human moon exploration. But the legacy of Apollo lives on. In every reflective visor selfie an astronaut took on the moon, our planet is seen small behind them, a humbling perspective gifted to us by those missions. Even as Apollo ended, robotic explorers were gearing up to tour the outer solar system and its moons. In 1979, NASA's twin Voyager spacecraft flew past Jupiter and then Saturn. Voyager 1's cameras, as it swung by Jupiter, captured something astonishing: active volcanoes on Io, the first proof of active volcanism beyond Earth. It was a discovery that made scientists gasp. Until that moment, we assumed moons would be cold and dead. Voyager also sent back tantalizing images of Europa's cracked ice shell and hints of complex surfaces on Ganymede and Callisto. At Saturn, Voyager 1 and 2 revealed Titan's thick, smoggy atmosphere and the spongy Hyperion, and many of Saturn's smaller moons in detail for the first time. These brief flybys were like flipping through a cosmic photo album, each image raising new questions. They paved the way for longer visits. In the 1990s, NASA's Galileo spacecraft became the first to orbit Jupiter. Galileo spent 8 years in the Jovian system, repeatedly flying by the Galilean moons. It confirmed that Europa likely harbors an ocean beneath its ice, photographed Europa's ridges and chaotic terrains up close, and even saw what looked like rafts of ice that had broken and shifted. Galileo also found evidence that Ganymede has its own magnetic field, and hinted that Callisto might have a subsurface ocean too. Meanwhile, Galileo watched Eo's volcanoes in action, seeing plumes and red glowing lava, and mapped the resulting changes. This extended exploration turned those moons from curiosities into richly studied worlds. Galileo, however, suffered a stuck antenna, which limited the data return, yet still transformed our understanding of Jupiter's moons. Around the same time, attention turned back to Saturn. The Cassini-Huygens mission, a collaboration between NASA, ESA, and others, launched in 1997 and arrived at Saturn in 2004. For 13 years, Cassini orbited Saturn, a marvel of longevity and discovery. It carried a passenger, the Huygens probe, which in 2005 descended through Titan's atmosphere and landed on Titan's surface, the first landing on a moon beyond our own. Huygens sent back images from beneath Titan's orange sky, rounded icy rocks, a damp riverbed, and a horizon shrouded in fog. It was like standing on a primordial Earth, bitterly cold and alien, yet eerily familiar in geomorphology. Cassini, orbiting above, mapped Titan's surface with radar, revealing lakes and dunes, and it watched Titan's seasons change over the years. Cassini's tour of Saturn's moons was like a grand saga. It discovered the water plumes of Enceladus, flying through them to taste their composition. It imaged Enceladus's tiger stripes in detail and confirmed an ocean beneath its ice. It photographed Iapetus's two-tone divide and dramatic ridge, investigated Hyperion's chaotic tumble, saw jets of tiny moon Daphnis sculpting Saturn's rings, and even witnessed a meteorite crash into Saturn's rings, a tiny collision caught serendipitously. Cassini made hundreds of flybys of Saturn's moons, essentially writing the textbook on the Saturnian system. When Cassini's fuel grew low, NASA chose to end the mission by plunging Cassini into Saturn in 2017. In its final orbits, Cassini gave us unprecedented close-ups of the rings and measurements of Saturn's gravity, a fiery grand finale for an epic mission. As it disintegrated in Saturn's atmosphere, scientists and the public alike bid farewell to a venerable explorer that had, quite literally, broadened our horizons. After Cassini and Galileo, our explorations continued. New horizons flew by Pluto and Charon in 2015, revealing the surface of Charon, the moon half of that binary, in detail for the first time. Pluto's heart and mountains stole the show, but Charon's discovery of a giant chasm and a dark reddish cap of tholins at its pole added to the list of surprising moon geology. Even Neptune's moon Triton got another look, albeit distantly, with Voyager 2. We haven't returned since, but proposals exist to send an orbiter there in the future. Meanwhile, back to Earth's neighborhood, our moon saw renewed robotic visitors. Orbiters like NASA's Lunar Reconnaissance Orbiter, mapping it in high definition, and China's Chang'e program achieving soft landings, including on the far side. These missions found water ice in permanently shadowed craters at the lunar poles, a valuable resource for future explorers. They also continue scientific investigations of lunar geology and even biology experiments. Now we stand on the brink of a new wave of exploration. The era of returning to the moon and pushing farther to the outer moons with advanced probes. NASA's Artemis program is the flagship of human spaceflight in this realm. Named after Apollo's twin sister, Artemis aims to land the next man and the first woman on the moon, focusing on the lunar South Pole region where water ice resides in shadowed craters. Artemis I, an uncrewed test flight of the mighty Space Launch System rocket and Orion spacecraft, flew around the moon in 2022, heralding the return of NASA's crew, capable deep space vehicles. Artemis II will carry astronauts on a lunar flyby, and Artemis III, slated for the mid-2020s, hopes to put boots on lunar soil again. The plan is not just flags and footprints this time, but to establish a sustainable presence, perhaps a lunar base or the lunar gateway, to facilitate ongoing exploration. Living and working on the moon will serve as a test bed for eventual human missions to Mars. One can imagine future astronauts at the moon's south pole, sunlight skimming the horizon as they harvest ice for water and fuel, and look up to see the distant blue Earth and perhaps beyond it, glints of Jupiter or Saturn, moons gazing upon other moons. On the robotic front, one of the most anticipated missions is NASA's Europa Clipper, set to launch in the mid-2020s. This large spacecraft will orbit Jupiter and make dozens of close flybys of Europa, scanning its ice shell with radar, measuring its magnetic field to confirm the ocean's characteristics, imaging the surface at high resolution, and sniffing for any signs of plumes or organic molecules. Europa Clipper's goal is to assess Europa's habitability, essential groundwork, if we ever decide to drill through that ice or send a submarine into its ocean. Around the same time, the European Space Agency's JUICE mission, launched in 2023, is on its way. By 2030, JUICE will arrive at Jupiter and focus on Ganymede, while also studying Europa and Callisto in flybys. JUICE will give us an unprecedented look at Ganymede's magnetic field, its suspected ocean and surface. Looking further ahead, concepts are being studied for an Enceladus mission that would orbit or land on this tiny moon to directly search for signs of life, perhaps by sampling fresh plume material for complex organic compounds or even cell-like structures. Another mission, Dragonfly, is in development to go to Titan. This won a rotorcraft lander that will launch in 2027 and arrive in the mid-2030s. Dragonfly will hop between different sites on Titan's surface, investigating the chemistry of its dunes and possibly the edges of its methane seas, in search of prebiotic chemistry or even biosignatures, and to understand Titan's chemistry. Meanwhile, the Japanese Space Agency is preparing the Martian moon's exploration mission to Phobos. Scheduled to launch in the mid-2020s, MMX will land on Mars's moon Phobos, collect samples, and return them to Earth, aiming to reveal that moon's origins. Every mission to a moon brings new wonders. Cassini's findings of Enceladus's habitable ocean were not even on the radar when Cassini launched. We were taken completely by surprise. What surprises might Europa Clipper or Dragonfly or Artemis astronauts have in store? Perhaps plumes on Europa will reveal organic molecules more complex than any found off Earth so far. Perhaps Dragonfly will find that Titan's organic soup has formed something like primitive cell membranes or interesting electrical patterns in the hydrocarbon lakes. Maybe Artemis explorers will discover a new mineral in the lunar craters, or even microbial life hitchhiking from Earth that survived in lunar ice, giving cautionary data for planetary protection. These missions are not just about satisfying curiosity, they carry profound implications. If a future probe finds even microbial life on another moon, it would prove that life is not unique to Earth. If we find an absence of life in places that seem habitable, that too tells us something, that life might be rarer than we assume or needs more specific circumstances. Human missions like Artemis aim to make the moon a part of humanity's sphere, no longer an unattainable orb, but a place where people can work, research, and perhaps one day even mine resources or build observatories. There's also an emotional and cultural resonance to these explorations. Apollo's pale suits against grey dust became an icon of the 20th century. The image of Huygens landing on Titan, navigating by parachute down through orange clouds, fired imaginations about exploring alien skies. Each mission extends our senses. With cameras, we have stood on the slopes of mysterious mountains on the Moon and looked back at Earth. We have floated above Jupiter's swirling storms, with Io glowing in the foreground. We have watched a sunset on Titan through a hazy atmosphere. We voyage through our probes, living vicariously through their lens. As we continue to reach out, it's worth remembering that these endeavors are also acts of stewardship of knowledge. We learn not just about those moons, but about Earth by comparison, about how planets and moons interact. And these missions inspire generations. Some who watched Apollo or Voyager are today the ones designing Artemis and Europa Clipper. Our expedition through the history and future of moon exploration underscores a theme. Once unreachable, moons are now within our grasp. We have touched our moon, orbited others, and landed on a few. We have plans to return and even reside for a while. Robotic envoys will soon sniff the air of distant moons and crawl on their surfaces. It's an exhilarating time, blending the spirit of adventure with meticulous science. Equipped with all this knowledge and experience, our perspective shifts when we look up at the night sky now. We don't just see a bright moon, we see a place humans have stood and will stand again. We spot Jupiter as a point of light and imagine the pinpricks of Io's volcanoes or Europa's potential plumes. Saturn's golden dot brings to mind the lakes of Titan and the geysers of Enceladus. These celestial lights have become places in our minds. With our machines and dreams, we have brought the solar system's moons into our realm of experience, if not physical, then intellectual. And with each mission, we become a species not confined to one world, but a bit more at home in the vast archipelago of worlds that orbits our sun. Now, beyond our sun, countless other stars shine in the night. Around many of those stars orbit planets, and around some of those planets, perhaps moons. Before concluding our journey, let us cast our gaze even farther, to the possibility of moons circling distant exoplanets, and consider what their existence might mean. Moons beyond our solar system, the quest for exomoons. So far, our tale has stayed within the bounds of our sun's family. But even as we explored the moons of our solar system, astronomers have been pondering a tantalizing question. Do moons exist around planets of other stars? We call such hypothetical worlds exomoons, and finding them is an ongoing quest at the cutting edge of astronomy. If planets are common in the galaxy, it stands to reason that many of those planets, especially the giant ones, should have moons. Perhaps some alien sky has a view as lovely as Jupiter and its retinue. Or perhaps an Earth, like exomoon, orbits a huge planet in a distant star's habitable zone, providing a home for life. Detecting exomoons is, however, even more challenging than detecting exoplanets. Planets themselves often are found indirectly, for example, when they transit their star and cause a tiny dimming of starlight, or when their gravity makes a star wobble. A moon is smaller still, and its effects subtler. Nonetheless, scientists have devised clever ways to hunt for them. One method is to look for slight irregularities in a planet's transit timing or duration. An unseen moon tugging on the planet could cause it to wobble and transit a bit early or late, or produce extra dips in starlight. Another approach is direct imaging. A few large exoplanets have been photographed around stars. A sufficiently large and well-separated moon might one day be directly observed in such images. In 2018, researchers announced the first compelling exomoon candidate. Using data from the Kepler Space Telescope, they studied a Jupiter-sized exoplanet called Kepler 1625b, around 8,000 light-years away. They noticed hints that this planet's transit was followed by a smaller dip, possibly a Neptune-sized moon trailing the planet. Follow-up observations with the Hubble telescope added evidence that something was there, although the result remains unconfirmed and debated. If real, this exomoon would be far larger relative to its planet than any in our solar system, a reminder that exoplanets continue to surprise us with their diversity. In 2022, another possible exomoon was reported, also quite large, though it too awaits confirmation. Why the focus on giant moons? Simply because our current techniques are sensitive enough only to detect very large moons, likely gaseous or icy, around big planets. We don't yet have the capability to find an exomoon akin to our moon around a distant Earth-like planet. But as technology improves, through new space telescopes and more sensitive instruments, astronomers hope to eventually detect smaller exomoons, perhaps even down to the size of Mars or Earth. The implications of exomoons are exciting. Some scientists argue that an Earth-sized moon orbiting a gas giant in the habitable zone of a star could be a habitable world itself, essentially a moon planet with conditions for life. This scenario, reminiscent of science fiction locales like the forest moon of Endor in Star Wars, is scientifically plausible. A large moon could have an atmosphere, liquid water, and stable environments, all while orbiting a protective big planet. The presence of a giant planet could even shield the moon from excessive asteroid impacts or provide a magnetic field umbrella. On the other hand, it might also bathe the moon in radiation, posing challenges for life on the surface, but perhaps life could thrive underground or underwater. Exomoons also broaden our perspective on where life might arise. We now know to look not just at planets, but their moons. In our solar system, we see potentially life-friendly environments on moons like Europa and Enceladus. If similar moons exist elsewhere, the galaxy's habitable real estate could be significantly expanded. A star's habitable zone might contain giant planets that themselves are inhospitable gas balls, but their moons could be the true gems. The search for exomoons is a testament to our desire to not only find analogues of our planet, but also analogues of our moon and the rich relationships that moons have with their primaries. It forces us to refine techniques and maybe even build future observatories dedicated to this faint whisper of a signal. Perhaps in the coming decades, we will get our first confirmed detection of an exomoon. And if we are truly fortunate, one day we might even glean information about its atmosphere or composition, enough to say, for instance, this moon has oceans and clouds. The existence of exomoons, confirmed or not, also has a philosophical tinge. It underscores that our solar system is not unique in its complexity. The dance of planets and moons is likely a common cosmic theme. Somewhere out there are moons that cause eclipses as seen from their planets' surfaces, moons that tug tides on alien oceans, moons that might glow with bioluminescent life under foreign skies. We have begun to suspect their presence. The next generation of telescopes will no doubt reveal them one by one. When we finally do find them, exomoons will become part of our ever-expanding narrative of the cosmos. Each new moon discovered around a distant sun will be a reminder that nature's creativity is boundless. The moonlit nights we know on Earth, so special to us, might be a universal experience shared under many skies. And knowing that adds a profound connection. The same way every human culture under our moon found meaning in its glow, perhaps across the galaxy, other beings dance under the light of their moons. For now, exomoons remain a frontier, a promising echo of the familiar in the vast unknown. As our documentary journey transitions from exploring the known moons to reflecting on their meaning, the possibility of exomoons serves as a bridge. It links the concrete knowledge we have gained about moons in our solar system with the tantalizing potential of worlds yet to be discovered, out beyond our reach, but not beyond our imagination. Reflections. Under alien moons, meaning and metaphor. Throughout history, the moon has been a mirror, not just of sunlight, but of human thought and emotion. We have cast our dreams, fears, and philosophies onto that gentle disk in the night. Now, having journeyed among the moons of the solar system, we return with a richer tapestry of meaning. We see that every moon, in its own way, is a symbol, and their stories resonate with our own. From our earliest days, the moon was a companion in the dark, a source of wonder and reassurance. It waxed and waned, teaching us about cycles, the idea that endings are not final, for the crescent grows again after the new moon's darkness. In this, people found hope and rhythm. The moon became associated with the cyclical nature of life, time measured in moonths, the tide, like flow of fortunes, the rhythms of fertility and growth. Poets compared the waxing moon to a growing child or the blossoming of love, and the waning moon to aging or heartbreak, yet promised renewal in the next cycle. Nearly every culture saw something personal in the moon's face. Some saw a compassionate figure, a goddess who lights the night and watches over lovers and lost travelers. Others saw a clever god, or a mischievous rabbit, or a reminder of heroic stories. These myths, diverse as they are, share a sense of the moon as an object of connection between the heavens and human hearts. The moon was distant, yet felt intimately close, influencing daily life through calendars and tides, and nightly life through its calming glow. It symbolized the known in the unknown, a gentle light amidst darkness. Now consider our new knowledge. Moons are everywhere, not just orbiting Earth. Each planet has its own moonlight in its sky, its own tidal rhythms imposed by orbiting companions. The idea that moons are silent watchers extends beyond Earth. One can imagine a hypothetical being on Jupiter's cloud tops marveling at the dance of Io and Europa, or a being on Titan witnessing Saturn's rings casting shadows in Titan's sky, with tiny Enceladus sparkling as a star, like point. The presence of moons is a universal feature of planetary systems, which suggests something profound. The concept of a smaller body, forever bound to a larger one, is a motif written into the cosmos. It invites metaphor. Are we not all, in some sense, moons? We live our lives influenced by greater forces, the gravity of our communities, our nations, our planet, the sun's energy, the pull of tradition and history. Yet within those orbits, we have our own trajectories, our own landscapes and individuality. To be a moon is to be a follower, a companion. But our exploration has shown that a companion world is still a world. Being gravitationally bound to a planet doesn't diminish a moon's uniqueness. In fact, that relationship can enrich it. Tidal heating can endow it with fire and ocean. Tidal locking gives it a permanent sky view of its primary and perhaps a special stability. In the same way, perhaps being bound to greater things, family, society, the Earth itself, does not diminish individuality, but provides context that allows life and meaning to flourish. Moons, by their very existence, teach a lesson of belonging. No moon floats alone in space. Each is part of a system, just as we are all part of something larger, be it family, culture, or the biosphere. And yet, moons also teach resilience and identity. Think of Triton, captured against its will, retrograde and rebellious. Yet it settled and became one of the most intriguing moons we know, forging geysers under Neptune's distant sunlight. Or Europa and Enceladus, tiny in comparison to their planets, yet possibly cradling more life potential in their hidden seas than the huge worlds they orbit. Size and rank do not correlate with significance. A small moon can have a global ocean. A giant planet might be a sterile gas ball. Likewise, a single human or small community can harbor creativity, love, and innovation that influence the larger world profoundly. The relationship is symbiotic. The big influences the small, and the small can influence the big. The moon has also always symbolized reflection. It shines, but with borrowed light. In that, there is a deep metaphor. We too shine often with light passed to us by others, knowledge, wisdom, kindness that we have received, and then reflect onwards. Our ideas are illuminated by the great thinkers before us. Our compassion is lit by the love we've been shown. And like the moon, which can cast enough light to show the way in darkness, we too can reflect the light of greater truths or greater goodness into the dark corners of each other's lives. We might also think of the moon as representing the idea of being secondary, yet essential. Planets dominate their moons in gravity, but if you remove the moon, the system changes drastically. Earth without its moon might not have fostered such stable, life-friendly conditions. Jupiter, without its Galilean moons, would lack the most interesting aspects of its identity. In the same way, what orbits around a person or a society, its art, its ideas, its satellites of influence, though secondary in mass or power, might be what truly defines it. A planet without moons is a bit like a leader without companions or a mind without dreams, functional but missing depth and nuance. Consider also the perspective of standing on a moon looking up at its planet. On the moon, astronauts gazed up and saw Earth, a swirling orb of blues and whites, a sight that moved them to profound introspection. On Io or Europa, one would see Jupiter's banded enormity filling the sky, a constant reminder of a bigger presence. Perhaps this is akin to moments in human life when we stand in awe of something larger than ourselves, standing before the vast ocean or a towering mountain, or contemplating the galaxy on a starry night. We feel small, yet connected to something grand. Moons literally live with that view every day. They know, if one can poetically assign knowledge to them, what it means to always circle something awe-inspiring and bigger. But they also show that one can have one's own identity in that situation. The people of ancient times could look at the moon and feel both the greatness of the heavens and the personal comfort of that lantern in the sky. There's a balance there of humility and significance. Culturally, the moon often symbolizes the subconscious or the hidden, as the sun symbolizes the obvious and conscious. The moon comes out when the sun leaves, revealing stars, hinting at mysteries. Likewise, exploring the moons of the solar system has been an exercise in illuminating the previously unseen, delving into the mysteries of how diverse nature can be and holding a mirror to our assumptions. Who would have expected that desolate-looking Europa would hide a deep ocean, or that tiny Enceladus would shoot geysers into space, visible to Cassini's cameras? These discoveries were like subconscious truths emerging, showing that reality is richer than daylight logic might predict. We as a species are enriched by these revelations. They remind us to keep an open mind and appreciate the unseen forces and potentials in our own lives and world. The phrase orbiting something greater resonates beyond astronomy. Philosophically, it speaks to a relationship between part and whole, self and other, finite and infinite. We on Earth orbit the sun, a star that gives us life. The sun orbits the center of the galaxy. Perhaps even galaxies orbit some center in a cosmic dance. At every scale, orbiting something greater is the rule. It does not diminish the smaller. Instead, it binds systems together in a dynamic balance. One could poeticize that electrons orbit atomic nuclei, and in doing so, create the atoms that build everything tangible. It's orbiting that allows structure, so being in orbit is not a subservient act. It's a creative one that allows complex structures and stability. Without orbiting, without relationships of gravitation and revolution, the universe would be a diffuse, structureless haze. Likewise, in human existence, binding oneself to ideals, causes, or communities greater than oneself can give structure and meaning to life. We orbit principles of justice, love, or curiosity, and that orbit guides us and gives our journey shape. Standing under the night sky now, we no longer see moons as mere lights or dots. We see destinations that humans and our robotic envoys have touched. We also see stories. The moon is no longer just Apollo's goal, but Artemis's next foothold, and a muse for humanity's future. The moons of Jupiter are no longer just Galileo's tiny points. They are volcanic Io, oceanic Europa, massive Ganymede, ancient Callisto, each a world to marvel. We are connected to them now by knowledge and by the anticipation of discovery. When we behold Saturn through a telescope and spot Titan as a faint dot, we know there's an Earth like sky there, and perhaps we feel a kinship with whatever chemistry is brewing on its surface. In a sense, through exploration, all these moons have become extensions of our mental world. Our human story has expanded to include them. We've left footprints on one, tire tracks on another, probe markings on Titan's frozen ground. We've made these distant places, in some measure, part of our shared human experience. And as we did so, we found that those places were not barren in meaning. They reciprocated by teaching us about ourselves. They taught us patience, taught us humility, taught us unity. In mythology, the moon often represented the feminine, the cyclical, the responsive, complementing the sun's masculine, steady output in many cultures. One could say the moons of the solar system collectively represent the yin to the planet's yang, the supportive, nurturing side of planetary systems. They stir tides, they may nurture life in their oceans, they moderate axes and climates. And philosophically, maybe we as humanity play a moon-like role in relation to our planet, nurturing it by reflecting the light of knowledge and awareness onto it. We have the power to bring unconscious processes into consciousness and address them, much as the moon's light allows us to navigate the dark. Finally, consider the sheer beauty and improbability of it all. In a universe that may be mostly empty, here we are in a system with a wealth of moons, where one tiny rocky sphere can orbit a gas giant and harbor a subsurface sea that might host alien microbes, or where a dead-looking moon turns out to have cryovolcanoes that paint its surface. Is this not wondrous? It speaks to an inherent creativity in nature. In that, some find spiritual meaning, seeing in the proliferation of moons and their diverse stories a sort of cosmic art, an expression of what some might call the divine, or simply the boundless creativity of physics. The moons invite us to think about companionship and solitude. Our Earth's moon has been a constant companion, night after night. Mars's little moons accompany it like faithful, if odd, shaped pets. Jupiter carries an entire miniature solar system, a reminder that even in the company of others, each member can be distinct and vital. As we humans venture out, possibly one day establishing bases on the moon or visiting Mars, we too become companions to these moons, integrating ourselves into the cosmic neighborhood as participants, not mere observers. In closing our journey, we return to a simple scene, a person standing under a moonlit sky, gazing upward. Beyond the silhouette of our moon, our mind's eye knows there are other moons orbiting distant planets, shining in their skies. The night is richer now. We feel connected to something far beyond, as well as deeply rooted in our own world. The silent watchers of the night have shared with us their stories, and we find that they are our stories too. Stories of orbit and influence, of reflection and yearning. In their silent orbits, these moons, great and small, are indeed guardians of the night. They keep the stories of their planets and share their light with the darkness. As our journey ends, we look up with a deeper reverence. The night sky is alive with these silent companions, forever circling, forever reflecting. They inspire us to continue our cosmic dance of exploration, and under their watchful glow, we carry onward, seeking knowledge, seeking connection, and seeking our place among the stars.